All right, this is part 2. If you're watching the recorded version of this, stop what you're doing, go back, watch part 1. If you can't find it via whatever links you got from anybody else, you can find it on my website, tecmungo.com, and then go to training, and then go to online, and you'll find it there as well. All right, so watch part 1 first. That makes the most sense. This is part 2, but it is actually the 3rd week of doing this. The first week was a separate topic on ventilation and COVID and things like that. And then last week and this week, the topic is on energy saving systems for package systems. We are doing this in partnership with the Massachusetts Energy Efficiency Partnership and the folks over at UMass. So most of you guys are, because of that, located in Massachusetts. I know we got some folks in New Hampshire and New York, and some folks in the Midwest because they know who I am. But that's all okay. But it's all going to have a Massachusetts version to it, if you will. It's not showing the right screen again. Oh, there we go. So this is our agenda for part 2. Right, so for part 1, if you didn't know, we covered all kinds of basics on energy. We covered rooftop efficiency. We covered programmable thermostats. We covered economizers, stuff like that. Now we're picking up with this part, starting off with staged air volume systems for packaged rooftops, and even split systems that would apply as well. Then we're going to move into heat pumps. That's a very common topic now. And then we'll go into variable refrigerant flow systems. That'll be kind of our layout here for this morning. If you guys have any questions as we go on the live version, obviously, type them in that question chat box. I'm going to monitor that, and I'll do my best to address them as we're on that topic. I don't want you to wait 3 hours and then try to remember what you wanted to ask. Just ask it, and I'll try to address it every couple minutes. All right, so here we go. Our next topic is staged air volume systems. This guy has lots of different names depending on who you ask and what decade you ask people. So certain manufacturers call it single zone VAV. Some call it multi-stage air volume. And then back when I started in the 90s, we called it adaptive fan control. Lots of different nicknames for what is essentially the same thing. We're going to explain how that works. So this really got ramped up following a study in 2013, which to me feels like it was a year or two ago, but it's like almost a decade at this point. Before that, it was pretty uncommon for us to do staged air volume type systems. It was unique specialty applications where we did it. But after this study in 2013, it became fairly highly requested and then eventually became code required. And I'll explain all of that as well. But this study is kind of what kicked it off. So we're going to start off with this study as well. And I'm not going to read you a 200-page study because that would be literally the most boring thing I could think of. No offense to the folks at the lab here, but this is like the abbreviated version. So the purpose of this study was to figure out if I'm doing economizers and I'm doing demand control ventilation, which are things we've mentioned in the past couple of weeks, and I'm doing this multi-speed fan control, this staged air volume control, how much energy can I save by doing all of these things? Because these things are really fairly inexpensive ways to get more efficiency, and they are all things that can be retrofitted onto an existing rooftop unit. What I can't retrofit is, hey, just give me a higher SEER rating or a higher EER. Well, that takes a lot more coil surface area and things like that. That's not a retrofittable thing. But adding an economizer on, adding a CO2 sensor for demand ventilation, putting a fan speed control in, those are things I can do in the field fairly easily. So they did a bunch of energy modeling to figure out how much this stuff would save. And then they did field testing on 66 rooftops to verify that their models were correct and or tweak their models to make them more correct. And these units that were in the study were different geographic areas, different types of building usages, and different manufacturers, just trying to get a broad sample to see if they've been modeling it correctly the way they think they were. Most of the units are in this middle tonnage range, 10, 12.5, 15, 17.5 ton rooftop type things. That doesn't mean this technology won't work on a 5-ton rooftop. It absolutely will. It doesn't mean you can't do it on a 40-ton rooftop. You absolutely can. But that target range is kind of the sweet spot because that's the smaller the units are, the harder it is to make any energy saving things pay back because they're so small, they don't use that much energy, right? And the bigger units, there's just not a lot of volume of them, manufacturing wise and installation wise. So this middle range, 10, 12, 15 ton units, that's kind of the point where it does make a lot of financial sense and there's a lot of them in the market. One of the cool things about this study, if you think studies are cool, is that they collected data every single minute for the whole entire year. That's a ton of data to work with. But even cooler than that is that most studies have some inherent flaws. For example, if I want to see if a certain technology works, I got a couple ways I can do it. I can either measure your building now, its energy usage now, install my technology, and then measure the energy usage again, right? But that assumes nobody else has messed with anything. Like they didn't change anything, they didn't mess with set points, they didn't disable stuff, etc., etc. Or what I can do is I can take a bunch of buildings that don't have the technology and look at those, and then take a couple buildings that are very similar and put the technology in and look at those and then try to compare them. But that doesn't account for the ways that different occupants might behave and interact. So what this study did is different than both of those. Every day they switched it. So on Monday, we ran it the old way, if you will. On Tuesday, and I say we, I'm not the one doing this. This is the Pacific Northwest Lab guys. But on Monday, they ran it the old way. Tuesday, they ran it with the new controls. Wednesday, they put it back to the old way. Thursday, they put in the new control sequence. And every day, they flip the sequence back and forth. That way, they got 6 months of data for each scenario, but they got it over the same time frame. And any occupant things, like if an occupant messed with the thermostat or whatever, that's fine because it would apply to everything, not just one of those two sample studies. All right, in any case, these studies, when they first came out, the study was showing pretty good energy usage on the normal system. Normal system meaning it's an electric compressor rooftop unit with a gas-fired heat exchanger on it. And that was typically like 25, 30, 35% savings on those units. And then the heat pumps had even more potential for savings. We'll explain that as well. So of those things that were being studied, economizers, demand control ventilation, and fan energy savings, the most dominant of that savings dollars was the fan energy, which is interesting because the economizers we've been doing for decades. The CO2 demand ventilation, as you guys probably know from 2 weeks ago, I started doing it 20 years ago, and it became pretty mainstream like 15, 12 years ago, something like that. But the fan staging thing is fairly uncommon. But it was the biggest energy saver of the three, by far, like not even close. The study also had some simple paybacks that were illustrated for the readers of the study, showing what it would take to get paybacks of 6, 3, and 2 years, corresponding to 3 different utility rates of 5 cents, which I don't think is anybody anymore, 10 cents, and 15 cents per kilowatt hour. Those paybacks included the cost of the labor and the materials. As you would expect, the bigger the rooftop unit, the better the payback would be. Because I'm buying a certain kind of technology. I'm buying stuff. Economizers, economizer controllers, CO2 sensors, VFDs. And for the most part, that stuff costs the same on a 10-ton unit as it would cost on a 30-ton unit. It's a little bit more on a 30-ton unit, but it's pretty much the same. So the larger the unit, the more airflow I run through it, the faster the payback. Additionally, units that run longer run times had faster paybacks. If I'm only running a unit 10 hours a day, it's going to be harder to have a payback on any technology compared to a unit that's running 20 hours a day. So the larger the unit, the faster the payback. The longer the unit's running its occupied hours, the faster the payback. This study looked at 3 different manufacturers of control widgets to install and do this with. At that point in time, 8 years ago, there was only those 3. You could do those 3, or you could do like a totally custom building automation system, which is fine, but that's a little bit harder to just kind of, broadly define. So they looked at these 3. They ended up choosing this catalyst type system to do the study with. And just for the record, I don't work for Transformative Wave. I never worked for them. I've never even used their system, other than just playing with it in my lab. But I've never used it on projects, so I'm not like promoting them or anything. Just telling you that's the one that the national guys decided to use. All 3 of these vendors do similar things. They use VFDs to control the speed of the indoor blowers, and they don't do that like a traditional system where we track static pressure. Because on these simple rooftop, these simple constant volume systems, there is no static pressure changes. On a big VAV system, we have static pressure changes, right? As the zone dampers throttle back, it builds up static pressure. We can measure that and slow the VFD down. Well, these systems don't have anything that changes the static pressure. So we can't use any traditional control mechanisms for the VFD. So what they decided to do is to control the speed of the fan based on what mode it's in. Is it in the heating mode? Is it in the cooling mode? Is it in the ventilation mode? Is it in stage 2 of cooling? It's basically the same thing we've done on residential furnaces that have ECM motors for 20, 30 years. If you didn't realize it, like, the residential equipment has a significantly higher manufacturing volume than commercial equipment, so a lot of R&D money goes into that residential stuff. And then a lot of R&D money goes into the big chiller plants, because chiller plants are, controlling huge giant buildings. They're exciting. It's easy to get an end user to understand a payback scenario and do it. That middle group with the rooftop units, they get no R&D dollars. Nothing. But not nothing, I'm exaggerating, but they basically wait for something cool to happen residential and then they bring it up. Or they wait for something cool to happen commercial, large commercial, and then they bring it down into the rooftops. So in any case, this is a pretty well-defined sequence of operation for a residential ECM furnace. And using this VFD is just a way to bring it into the rooftop world. All three of these manufacturers also use integrated economizers, which are code required everywhere. They have the ability to do CO2 sensors, which was obviously part of this study. One of the manufacturers modulates the compressor speed. There's some difficulties in doing that. For one, the rooftop manufacturer nor the compressor manufacturer allows you to retrofit that on there. It's specifically prohibited by their warranty. That doesn't mean you can't do it. It just means they're not going to back you up. But we'll talk about different ways to control compressor speed anyway today as part of this discussion. All right, so in this study, when they're in the ventilation mode, which means there is no call for heat, no call for cooling, then they would put the fan at 40% of its design airflow. If they were in a call for cooling or heating, they would put it into 90% of its airflow. Just take it 10% down. If it was a two-stage unit, then they would put it in 75% for stage 1, 90% for stage 2. At no point in time do they put it at 100%. Ever. Never ran it at 100% again. Because it was pretty obvious from all these units just looking at the buildings and doing a quick calculation that every single one of them was oversized. And if you logged in with us on a prior week, you probably heard me already complain about oversized equipment, so I'm not going to dump on that topic again. Just know that almost every single rooftop, furnace, boiler, chiller, cooling tower, fan, pump, everything that you run into in the HVAC world, it's probably oversized, and it's likely that it's grossly oversized. So, in any case, all of these systems were able to be run at a lower airflow than their design airflow rate. For the CO2 sensing point, they used 1,000 parts per million. As you know from 2 weeks ago, that's pretty aggressive set point. You could probably, in most areas of the country, use 1,100 or 1,200, but they used 1,000. I shouldn't say aggressive, I'm sorry, conservative set point. 1,000 is pretty conservative. You could get more aggressive in most places and do 1,100, 1,150, 1,200, but it was conservative in this case. This kind of shows you the typical scenario on what it required to get a 3-year payback. And somebody doing the study decided that if I can get a 3-year payback, I should be able to convince most building users, building operators, building owners that this is a good idea to do. Right? They obviously want really fast paybacks, and some buildings will tolerate a higher payback. They'll be fine with a 5 or 7-year payback if it's like, I don't know, a university, and they know they're not going to be getting rid of this building anytime soon. They're going to be there for like another 100 years. So they can probably think about higher paybacks. But if you're a small business and you don't even know if you're going to be in business in 5 years, you probably want faster paybacks. So they decided to see what did it take to get a 3-year payback. As mentioned earlier, the units that are higher tonnage, they pay back faster than lower tonnage because they have more energy usage to begin with. So higher tonnage, faster payback. More run hours, faster payback. Then beyond that, we needed some utility incentives, some spiffs from the utility, if you will, to get the paybacks down below 3 years. So for example, if you had a 20-ton unit and it was operating 14 hours a day or more, you can get a 3-year payback, even if the utility rate is really low, 5 cents a kW, and the utility doesn't even give you any type of rebate at all. You could still get a 3-year payback. But if you took that same unit and only ran it 10 hours a day instead of 14, right? Now you're probably going to need, for some utility rates, you're probably going to need a little bit of a rebate to make that payback happen faster. And you go down to the real small units like 7.5 tons, right? With only 10 hours of runtime, you're going to need a pretty high rebate in order to make this happen, and people wanting to do it. or high utility rate, right? One of the two or both. This slide here, this is the last thing I have on that study, and then we'll move into a little bit more how it works. This is like literally my favorite thing from that study, which I know makes me sound dorky that I have a favorite thing from a 200-page study, but this is really eye-opening, and it's not information I didn't already know. It's just information I've never really visually looked at it before. So that's why I like this. So this is showing some of those rooftops in that study, and it's showing you how many hours during that year they spent in which modes. So down here in red is how much time they spent in heating. It's not a lot of time. I mean, it may feel like it, especially if you live in a cold climate like everybody on this webinar does. But even in the cold climates, you're spending 18–20% in the heating mode. And that doesn't mean you're spending 18–20% in the heating season. We're in that season for like 7 months. You're spending that much time in the heating mode. So if you have to take a given hour of time, how many minutes during that hour did you actually turn the burner on? Maybe you turned it on for 7–8 minutes and then shut it off, and then 15 minutes later it kicked on again, right? And then it ran for a little bit and shut off, right? So when you add all of that up for the course of the whole year, it's under 20% of the year that we're running the heating mode. Up here on top in blue is what we're running the compressors in, mechanical cooling. And it's kind of the same story depending on what climate zone you're in. You're running it 5, 10, 15, maybe 20% of the year you're running a compressor. Green was how many hours you were spending in economizer mode, right? If you remember from last week, that's me using the outdoor air to get free cooling instead of running a compressor. And then purple was integrated economizer, times we're using the economizer and the mechanical cooling. So it's cool enough to get some cooling from outside, say 65 degrees, but it's not cool enough to do it all by itself, and it still needs a compressor to help. If it's 55 degrees, economizer can do it all, right? But if it's 65, I probably need the economizer and the compressor. And then if it's like 75 degrees, I don't even want the outside air. I need to go all compressor at that point, right? So that all probably hopefully makes sense. The baby blue line in the middle is the eye-opening thing. Baby blue means all of the hours, all the occupied hours that I have to run this system that I am neither running heating or any version of those 3 cooling things I said. I'm doing nothing. I'm just bringing in fresh air for ventilation for occupancy code. It's a lot of hours. So what this tells me is I'm looking at this going, man, like we're doing a really good job. We're getting higher IERs, higher EERs, higher SEER ratings on the refrigeration system in these units. Right? The bogey keeps going up, and we keep making it more and more efficient. And maybe we can find a way to get a little bit more efficient on the gas heating side, although it's hard without going to a condensing heater, which is a whole nother discussion. But look at all the hours in the middle when I'm neither heating or cooling. Even if I'm a rock star at making it more efficient from a gas and compressor standpoint, how do I get these hours to be more efficient? And that's where this fan control comes in, because the fan is running during everything on this chart, right? The heating's only running a little bit, the compressor's only running a little bit, but the fan is running all this time. Before we go to the next slide, let's see a couple of the questions that people just typed in. Mike says, can you explain 28 pre and 28 post? What does 28 mean? Okay, sorry about that. This is from that same study we've been talking about from Pacific Northwest National Labs, nationwide study. 28 was just a building number. 39 was a building number. 40 was a building number. So these were just some of the sample building numbers that they pulled out. So I don't recall exactly without looking at the study, but I think they tried to pull one out from like each geography and throw it up on the chart here. Because there were 66 total units. That's just what the number means. Pre means what the total energy usage scenario was before they did the control sequence, and post means after the control sequence. So if you look at like just this first example 1, so they're getting some heating savings on here as well, because if I'm slowing down the fan speed, I could have an inadvertent heating savings, and we'll illustrate that as well. There's also some scenarios where I have more heating costs by slowing the fan down, and I'll also show you that example. But usually there's a savings there. But the biggest part that comes from this heating savings, that's coming mostly from demand control ventilation, right? So that was where I used the CO2 sensors to determine occupancy. If everybody doesn't show up to work, I throttle their ventilation damper back. When I throttle their ventilation damper back, I'm going to have less heat needed to heat the outside air, so I'm going to get a gas savings. Right? And the cooling savings is coming from both demand control ventilation and from using the economizer on here. So you can see, like, for example, on number 39, green was my economizer 4. It was barely being used. Now I'm getting a lot more economizer operation hours out of here. And a lot of that is due to the fact that I need less cooling because I'm running demand control ventilation, and or because the original economizer wasn't set up correctly on the building, and now it is set up correctly. Let's see what else there was in there. A lot of ventilation hours, but fan energy is 15% of the overall energy. Compressors are the energy hog. Compressors are the energy hog historically, but as we're getting the units more and more and more efficient, the compressor portion of the total energy is getting smaller and smaller and smaller and smaller. And we can keep picking on the compressor and keep making it more and more efficient, which we've been doing. But at some point, we need to pick on something else. And that something else is now time to pick on the fan. So I'm not saying don't save energy on the compressor. I'm saying do that, but let's also start being more efficient with the fan, as well as the heating, right? All right, let's keep moving. So the three ways that we have currently available to us on a modern system to control the fan on a packaged rooftop or a packaged split system would be VAV, Variable Air Volume. This has been around from the 1960s. If you want more information on that, I can send you a whole 2-hour recording on VAV. I believe I have that somewhere. In fact, I should probably mention that right now too. I'm probably going to promise you lots of things like, hey, if you want to learn more about this, I got a recording on that. Hey, if you want to learn more about that, I got some slides or cheat sheets on that. If I say something like that and you want that particular thing, just send me a note. I'll put my email back up again, but it's Ryan, RYAN, .Hoger, HOGER, at TEC, that stands for Temperature Equipment Corp, TECmungo, MUNGO.com. Send me an email and say, hey, you said you had blah, blah, blah. Can you send it to me? And then I'll send it over to you. Because I'm not going to remember what I promised to whom and when. I'm going to forget by the time we're done with this in 3 hours. All right, so if you need more help on VAV, I can help you with that. But that is a zone system where you have dampers in the duct. Those dampers are responding to temperatures of individual rooms, and then we're using those guys to control the room temperature. And then I have a main air handling system that's providing air to all of them. That's a totally different category than we're talking about today, but that's a well-established system for decades and decades. The bottom one, CAV, Constant Air Volume, is also a well-established system. This is your everyday system. The fan just turns on, it goes to one speed, that's all it does. What we're talking about today is the middle, Staged Air Volume. Down below is the typical sequence of a staged air volume unit that are available from the vast majority of manufacturers. And they all use the same sequence, and the reason they use this sequence is because starting in 2010, in ASHRAE Standard 90.1, which is the energy standard for the country, this is the sequence that energy standard required. So when they all started doing it, they all did it per that energy standard. Can you do it better than this? Yeah, you probably can. But most people just do it this way because this is the way that's already laid out. All right, so the way this basically works, I have 2 fan speeds and only 2 fan speeds. Would I like to have 3? Yeah. Would I like to have 5? Sure. But I only have 2. And the reason I have 2 is because the economizer controller is going to force me to only have 2 fan speeds, even though my VFD could do many more. And I will explain why the economizer controller is the limiting factor right now. But for right now, at the moment, just believe that part. So I got 2 fan speeds to work with. So what we're going to do is when I'm in ventilation only mode, baby blue over here, I'm going to go down to 67% of fan speed, right? I want that to be one of the lower fan speed choices because that's a lot of the hours. So I'm going to do that. If I'm on stage 1 of cooling, I want that to be 67% fan speed because that is actually required by the ASHRAE standard. If I'm in 2 stages of cooling, give me the full design airflow because that's obviously what I designed the whole thing for to begin with, so that's the time I need the full airflow. So stage 2 of cooling, I'm at full airflow. When I stage down to just 1 stage of cooling, I go to the reduced airflow. If I'm in ventilation only mode, I also use the reduced airflow. And if I'm in heating, which is not addressed by the standards at all, I'm going to go to the full airflow. Generally because if I chose the 67% airflow, it would not be sufficient enough airflow for me to keep the heat exchanger online without tripping high limit. So could I do it with 83 or 86% or something like that? Probably, but I only have 2 fan speeds to work with right now. So I'm going to choose to do it at the full fan speed because the lower fan speed is not going to cut it. All right, does that make sense? Anybody have questions on that? If I'm in ventilation only mode, meaning no heating and no cooling at the moment, low fan. If I'm in stage 1 of cooling, low fan. If I go to high stage cooling, full fan. And if I go to heating, full fan. Now, you don't have to do this with a VFD. There are lots of ways you can do this. You could use a 2-speed motor, and that's something that's available in the market and has been for decades. The problem with 2-speed motors is they have double the windings in them, right? So they're fairly expensive to manufacture. And, decades ago, you would have done it that way. But the cost of VFDs, variable frequency drives, has gone down and down and down over the past 20 years. And the reliability of those things has gone up and up and up. So it's now less expensive to get a regular single-speed motor and retrofit a VFD onto it versus buying a 2-speed motor with no VFD. So that's why we're typically using a VFD. Additionally, it doesn't have to be a VFD. When we get to the smaller units, typically 3-ton, 4-ton, 5-ton, maybe 6-ton, instead of using a VFD and a AC motor, we might use an ECM motor. That would be a DC motor. So instead of AC power, it's DC powered. And ECM stands for electrically commutated motor. As mentioned earlier, we've been using these in furnaces for decades, so they are readily available for systems that move the type of airflow that a 3, 4, 5-ton unit would move. So those guys have the ability to have multiple fan speeds controlled into them. So instead of putting a VFD on a regular motor, I can get one of those ECMs and do it that way. And that is a fairly popular way to do this on the smaller tonnage units. Mike is saying, question mark, go to heating full fan. That would increase the ACH, air changes per hour, reducing impact from internal heating sources, which require more HVAC heating. I don't know what you mean by that, Mike. I don't know. Require more than what? If I'm at the, are you comparing it to a regular system? Compared to a regular system, a normal everyday system without staged air volume, so a constant volume system, I'm already going to be at 100% fan speed for heating. So it's not going to cost me any more or any less money to run a staged air volume system where I reduce the airflow for cooling and ventilation. It won't cost me any more money on the heating side of the equation. So I'm not sure what you mean in that particular case. Ryan said, I thought you said high speed would be 90%, never 100. Yes. Okay, so let me clarify that. On this study from Pacific Northwest National Labs, on the 66 existing systems that they retrofitted, they found that none of the systems needed the full airflow that they were designed for. They were all over-designed. So they decided to reduce the airflow on all of them. And instead of giving them all different reductions of 88%, 90%, 72%, they just went with 90%, which meant the closest to correctly sized system was 10% oversized. The other ones are probably even worse. So that 90% was those particular studies. The ASHRAE 90.1 standard, the energy standard, is making the assumption that you're not doing things wrong and that you're not oversizing the system, right? So you can do it at 100%. Now, with that being said, the 100% on here is not 100% of what the fan could do. It's not the maximum that it can handle. It is 100% of the design airflow. So, for example, you may have a system where you designed it for maybe it's a 10-ton system. I'll make the math easy, and you designed it to do 3,600 CFM of airflow, and maybe the motor that you're putting in there can do 4,000. I don't run it at 4,000. I run it at 3,600. So it's 100% of the design airflow, not 100% of the unit's capabilities. And then we drop down to 67% of the design airflow on those lower scenarios. Mike says VAV heating CFM about 40 to 505 airflow than cooling. Oh, he changes his note. Heating airflow is 40 to 50% of cooling. So I'm not even sure what you're getting at, Mike. We're not talking about VAV today. That's going to be a different debate for a different day. I did mention it earlier just as a point of reference, but we're going to stick on stage air volume. So what you need to do on those, if you're trying to figure out how low you can go on heating, and you can go below 100%, how low you can go on heating, you have to look at the manual for that particular unit that you have, and those are typically just 1 and 2 stage units. You're not going to be able to do a separate airflow for heating from cooling anyway on any of these systems. But if you designed your own control system and you wanted to do a separate airflow for heating, you'd have to look at the manual, find out what the minimum allowed CFM is. Every single unit will have that published in their product data manual. Figure out what the minimum allowed CFM is and do it that way. It's going to be different for each model of unit. It's not going to matter anyway, Mike, because when we get to the economizer, you're going to see that I'm not even going to be able to have a separate airflow set point for the heating than cooling on a package system. But if you were doing a building automation controlled system with your own stuff, then you could do it, but you'd have to look at the manual to figure that out. If anyone needs help with that, let me know. Mike, we're using 100. Mike asked again, why are we using 100 for the heating? The only way I can explain it to you for right now is that we have to wait a little bit today to get to the economizer section. But I'll give you the short answer. The economizer only has 2 minimum damper positions. None of the packaged economizer controllers can do 3 or 4 minimums. They can only do 2. And if I have one for 100 and one for 67%, there's no longer any more minimum damper positions on the economizer to use with a third speed for heating. So that's why I'm restrained to only 2 speeds. If you could run your heating at 67% of the airflow, that would be fine. But most systems can't handle that. All right, so VFDs in general, just so everybody's on the same page, in case you're not familiar, you probably are, because most of you guys are energy conservation lovers, so you probably heard of VFDs. But it stands for Variable Frequency Drive. Sometimes generically you'll see them listed as VSD, Variable Speed Drive, and VSD would be a larger umbrella that would include VFDs, and it would also include variable speed ECMs and whatever else you can come up with. So VSD is just a generic way to say, hey, we're going to control the speed. VFD is the common way we're going to do it for mid to large size fans and pumps. So what it's going to do is vary the amount of power input to the system. As mentioned earlier, most fans are oversized. Statistically, I'm pulling this data from a Johns Hopkins study, but statistically, fan systems in the United States are oversized by 60%, which is pretty bad. That means that there's somebody out there who didn't oversize their fan. It's actually the right size. So to get an average of 60, that means there's somebody else that's like 100 or 150% oversized. So it does get pretty bad. If I took just a general motor, it doesn't even matter what it is at this point. It could be a fan, a pump, whatever. A general motor with a centrifugal fan or pump on it. And I'm running it at 100% speed. And let's just say it costs $1,000 a month. This is a pretty big ass fan. Costs $1,000 a month to run. If I dropped it down to 75% speed, how much would you expect it to cost to run? Anybody got a suggestion they want to type in? What they think that would cost? If 100% airflow is $1,000, what does 75% airflow get me? Mike's got a good guess. His guess is really good, so I won't say until somebody else guesses. No other guesses? Come on, you guys are boring. Throw something out there. What would most people say? Or if I asked the same question to one of my kids or to my spouse, they would likely say, well, if $1,000 is 100%, I'm going to expect to see 750. Okay, a bunch of you guys type 750, and that's kind of the answer I was looking for. Because that would be the logical thing. Hey, you drop it 25%, you're going to drop it 25% of the dollars. That would be the logical thing, but that's actually not going to be the case. We're going to drop it down to about $400. That sounds way better than 750. At 750, people would have said, yeah, let's do that. It's a good idea. At 400, it's a really good idea. If I cut the airflow in half, you obviously know the answer is not 500 in this case, because duh. Down to $125. This is due to something we call the fan laws, or if you're a pump manufacturer, you call it the pump laws. And if you do both, you call it the affinity laws. So you can play nice with both the fan guys and the pump guys. But any centrifugal fan or centrifugal pump is going to follow these affinity laws. And we'll give you the cliff notes on how the affinity laws work here in a minute. But the reduction, a little reduction in speed is a lot of reduction in money. So if I can get something, even in that study, get that something from 90% or 100% down to 90%, it starts adding up to be some pretty significant dollars with very little, effort. The other nice thing about using a VFD as my fan speed control is it's a very nice motor starter, right? I'm sure you've all seen constant volume systems, either the furnace at your house or the rooftop at your office building or whatever, and it turns on. You first hear it turn on, you hear it bang on, you hear all the ductwork canning, expanding, like ding, you hear all that noise, you hear belts squealing. All that noise is representative of the fact that there's a lot of stress on those mechanical components. A VFD doesn't just boom, bang on and everything's on, right? It's a slow start. It ramps up slowly. So a regular system is like your 17-year-old driving your car. A VFD is like you, an old person, driving the car. If anybody's 17 on this call, then you probably have no idea what I'm talking about, right? But the 17-year-old, or at least when I was 17, the way I drove is when the light turned green, gas pedal went to the floor, I just ran that thing as fast as I could get it to go until I got to the next stoplight. Then I slammed on the brakes, right? Nowadays, the way I drive is the light turns green. I slowly take my foot off the brake. I slowly press it on the accelerator. I start ramping up. People are going around me. I'm looking at the gauge on my car that says my miles per gallon instead of looking at my speed gauge because I'm cheap and I'm trying to save energy. And then I get closer to the stoplight. I'm kind of eyeballing it. Oh, it just turned red. I better coast to a slow stop. I drive way different at 45 than I did when I was 17, right? In fact, when I was 17, tires and brakes on my car would last me less than a year and a half. It was pretty bad. Now, the car I drive now, I had it since 2013. I just finally got new tires last year, and I have 150,000 miles on it, right? I got new brakes at like 120,000 miles. I don't use my brakes and tires as roughly as I used to. Well, VFD is the same way. It's going to slowly ramp things up, slowly ramp things down. There's much less wear and tear on belts and other components in the system. Paybacks on VFDs in general, as a general statement, are usually pretty good. 18 months is a pretty common thing you'll see people quoting. If you got a little tiny fan or pump, right, it's going to take more than 18 months. If you got a really big fan, it may take you 3-4 months to pay it back. It could be pretty fast. We talked about demand charges last week, so I threw this slide in today just to kind of help with that, right? Demand charges were part of our utility bill. We're paying for all of the large spikes in kilowatts that I need versus my long-term energy usage in kilowatt hours. So VFDs can help with my overall strategy for reducing demand charges. When I first turn an inductive load on, the amperage spikes up really high and then it kind of settles off. And this is a pretty extreme drawing on here. It's not usually that much of a settle down, but it spikes up and then it would settle down. And you could do different kinds of soft starters to minimize that, but a VFD is the best because all of those other types of soft starters still have an inrush current that spikes up and then settles down. VFD never spikes up. It just ramps up slowly, and then it still settles out at approximately the same point. So it will help out with your demand charges in addition to wear and tear. All right, the affinity laws we were talking about, or the fan laws as we're going to call them right now because we're dealing with fans. One of those fan laws is this relationship between RPM, speed of the motor, and the brake horsepower, which corresponds to the kilowatts that I need to buy, and hence my money. So the thing to note is that the RPM varies as a cubic function compared to the brake horsepower. So what is that going to look like? On this chart over here on the right, on the bottom axis, we have the RPM, the speed of the blower wheel. And on the vertical axis, we have both the airflow, CFM, and the brake horsepower, which is how much money it costs me to run, if you will. So I'm over here at a RPM of 2 units, whatever the units are. Let's just say it's 2,000 RPM. I'm over here at 2,000 RPM. It's costing me 8 horsepower to do that, and I'm making 2 units of CFM. Let's just say that's 2,000 CFM, whatever it is. If I were to cut that guy in half, cut the wheel speed in half from 2 down to 1 over here, right at that point, you can see what happens to my airflow. My airflow gets cut in half. So the airflow and the RPM are directly related to each other. The amount of air I move and the speed at which I run the fan are directly related. If I cut one in half, the other goes in half, right? If I cut the RPM to 25%, the airflow goes down to 25%. But look at what happens with the horsepower, which is the kilowatt hours, which is the dollars I'm going to spend. If I cut the speed in half and the airflow goes in half, look what happens to this guy. He goes from 8 on the horsepower down to 1. He goes down to an 1/8 because of this cubic formula. If you guys aren't good at algebra or you don't want to do any algebra, we can solve that for you, right? In this case, brake horsepower and RPM1 are my initial starting points over here that I started at. And then brake horsepower 2 and RPM2 are my final points that I ended at for the purpose of this example. So when you solve that out for that second brake horsepower, by cutting my speed in this case by 1/3, I chopped 1/3 off of the speed. So I went from 100% down to 67%. It's a 69% reduction in brake horsepower, which is a 69% reduction in my energy cost. It's pretty dramatic, which is why this is a pretty good payback scenario to use. And we have tens of thousands of systems that are running at a constant volume fixed speed that don't need to be at that speed all the time. At some point of the day, they can be at a lower speed. I'm going to throw this in too, even though today's on packaged systems, but since I've mentioned pumps a few different times, retrofitting a VFD on a fan versus a pump is a very similar process. You could do the exact same thing we're talking about here on hot water boiler systems, on chill water systems. There's going to be all kinds of codes that come into effect there. We're going to do these more like we do a VAV airflow system, and we're going to control airflow based on pressure. If you guys need help with that, let me know. I can give you some notes on that. Someone named Reddy is asking about 3% impedance on the devices. Is there a 3 or 5% requirement? I don't know what that's in relation to in terms of this discussion, so I'm not sure what the impedance requirement is you're referring to. But there are some cheat notes to pay attention to if you want to put a VFD on a hydronic system. So you measure the pressure at the farthest coil. I put that in quotes. And if you guys only do package systems, you can ignore the next 3 minutes, right? It doesn't apply to you. You have to measure pressure at the farthest coil, and it's in quotes because that is the one that has the highest pressure drop. So it's probably the geographic farthest. But I might have one that's a little bit closer that had tons of elbows in the piping, and pressure-wise, it's the farthest. I need to put two-way valves at each zone. Three-way valves don't help because three-way valves have a bypass, so they never really change the pressure of the system, at least not significantly. And then I need to also have a flow meter to make sure I keep the minimum water flow going through the chiller plant, and I don't drop below that at any point in time. So if these are my chillers or boilers over here, and they have their own little circulating pumps to make sure I get the required water flow through them. If I do that, I don't have to babysit this minimum flow. So if I'm doing a primary, secondary, I would do fixed flow in the primary, constant speed, and I do variable flow in the secondary, and I have all these coils out there. This is just showing 3 of them, but I might have 30 or 300 coils out there. I need to measure pressure over here at the furthest one and control the pump speed for that. If I can get enough pressure to operate this terminal over here, everybody upstream must be getting enough pressure too. That's why I control the farthest one. If you have a VAV airside system, which once again, that wasn't the focus of today, but I'm just mentioning it, you would do it the same way you do the pumps. I have this VAV air handler or rooftop providing airflow to all of my zones. I have 4 zones in this example, but you could just as easily have 40 or 80 dampers on there. I would like to go ahead and measure the pressure over here at the furthest one, and if he's getting enough pressure, everybody upstream is. So as the system throttles down, zones throttle their dampers back because they don't need as much cooling. We measure that pressure and we ramp the fan down accordingly. A lot of guys won't measure the farthest damper. They'll just put the pressure sensor about 2/3 down the duct. That's a common rule of thumb from the 1970s and 80s that a lot of us do. The current code doesn't allow it to be that way, but still a lot of guys do it that way. There are some advantages to this kind of stuff that we are not going to be getting on the staged air volume version of it. For example, on a VAV system, I get diversity credit. If I have 40 zones, I can bank on the fact that all 40 zones aren't going to be wide open at the exact same moment in time. So I literally install a smaller tonnage unit. If you needed a 40-ton unit, I may install a 30-ton unit because I've calculated that we don't need the 40 tons all at the same moment. If I didn't have any zone dampers, then yeah, I would. But the fact that some of them are saying I don't want any cooling and throttling back, I can take a diversity credit and install smaller equipment. When we do the staged air volume system that we're talking about today for package systems, I cannot take the diversity credit because there are no zone dampers. So everybody's getting airflow equally. I can't send it to one room versus the other room. I do get the benefit of the fan energy reduction though. But instead of throttling it back based on pressure, I'm throttling it back based on the cooling staging down, or all cooling and all heating shutting off. Right, and some of these other ones you're familiar with for VAV system energy savings, those are specific to VAV, and they were not going to come into our staged air volume discussion. Right, because our staged air volume discussion, as a recap, only has 2 speeds. There's one speed for when I'm in vent-only mode, which is the majority of the day, or at least the various minutes of the day, adding up to a majority. It's at that low fan speed when I'm on stage 1 cooling, which, by the way, helps me a lot with my dehumidification. Having a lower airflow with only 1 compressor on is significantly better for dehumidification than having full airflow with just 1 compressor on. And then when it's really hot outside and I do need 2 compressors and they both turn on, then I go to full airflow. And then as mentioned before, I have full airflow for heating as well, because I only get 2 airflows to choose on this control system. I'd like to have another one at like 80% for heating, but I don't have that option. There's only 2 speeds. It can't handle the lowest speed, so I got to go to the full speed on that. Mark says, exponent 3 is theoretical. In practice, RTU typically 3 or somewhat less. With an AHU with many VAV, the exponent can be under 3, ranging down to 2. I don't know what the 3 and 2 is you're referring to. What's the exponent you're referring to? Did I say something about that? Did I mention something with a 3 or a 2 in it? You're talking about 3 and 2A valves? I'm not sure what you're asking, Mark. Maybe you can clarify a little bit, and then it'll probably pop in my head on what you mean. Affinity laws, okay. 3 and 2. You're talking about the cubic function here? Exponent 3 is theoretical. So what are you saying? You're saying that you're not going to get a reduction? You're saying you're only going to get a reduction of squared? I'm not sure why that would be. So I don't understand. You're saying somewhere between squared and cubed is the real answer in practice? Maybe we can have a side discussion. You can explain to me why that would be. But even if we assume that that is true and that I'm not getting a full cubic function here and I'm getting something between squared and cubed, it's still going to be a reduction that is not linear, and hence it's still going to be a faster benefit to slowing it down a little bit. All right. From a code standpoint, not that everybody loves code, and I'm not going to read you all the code sections because that would be super boring, but I put the whole section up here in case someone has a question. We got to dive a little deeper. But from an energy code standpoint, if you're on the 2018 International Energy Conservation Code, which Massachusetts is on, and any of my coworkers in Illinois that are listening, you're also on the same code as everybody in Massachusetts today. And there's like, I don't know, 30 states that are on this code already. If you're on that code, there's a section for fan air control. And part of that section I have highlighted in yellow here. And that is when I have the systems that are going to be operating in the fashion that we're talking about, which is I am not full VAV. That's down over here, right? Full VAV systems are different. I'm not VAV, but I have systems that are above 65,000 BTUs of DX cooling, which is the packaged rooftops and split systems that we're talking about. 65,000 BTUs is like a little more than 5 tons. 60,000 would be 5 tons. So we'll say more than 5 tons, I have to reduce the fan speed down to 66% when I'm on low cooling. That's a code requirement for the international code, which is what most of us do. If you have smaller systems, 5 tons and less, you do not have to do the fan staging. But 6 tons and more, you have to have fan staging. You're not allowed to put in a constant volume fan anymore. It's prohibited. If you do happen to have something with zone dampers on it, right, so like a VAV system like we were mentioning before, then you need to have modulating control on there, not just two-speed fan. But for the non-zone systems, 2-speed fans required. So for different manufacturers, there tends to be multiple products that they offer, right? Hardly any manufacturers just offer one thing, just like car manufacturers don't make just one car. So for each size unit, most manufacturers make either 2 or 3 different models of unit that are available, especially at these middle sizes that we're talking about here, which would be, 7 tons, 10 tons, 12 tons, 15 tons, 20 tons. There's typically 3 models available. So they make a code minimum unit. Like what's the worst thing we can legally build from an energy standpoint and still comply with code? Okay, let's build that. So they build that. And that code minimum is typically not the code minimum from the international 2018. It's typically like a 2012 or 2015 version because many states still allow that. So a code minimum unit is not even going to be something you can legally install in Massachusetts or in Illinois and a bunch of other states. But it's the code minimum for like one of the worst states, if you will. Then they make a mid-tier thing, which is typically an upgrade. It's not a giant upgrade from the code minimum, but it's typically an upgrade, gets you more efficiency. And then they make a high-tier unit, which is like the loaded, Cadillac, Mercedes type unit. It's got like every option that you'd ever want. It's the most efficient unit. It also has all the extra cool stuff where the doors on it have hinges, and it has, a control system built in, all the great stuff, right? All built into one unit kind of thing. These bars on here are trying to help us represent, this is for one specific manufacturer, but we're just using it conceptually right now. These bars are trying to help us represent how we're getting to that efficiency. So for small stuff, if you remember from last week, small stuff meaning 5 tons and under, it gets rated in SEER, which is the residential efficiency standard, right? So that small stuff, those are those blue bars on here. We're mainly talking about stuff bigger than 5 tons today, so we don't really need to focus on that. EER, if you remember from last week, is the full load efficiency. How efficient are you when we max this unit out? We run it at absolute maximum capacity. How efficient is it? And then IEER was the part load efficiency. And we said last week that that was more important, that we spend a lot of hours at part load on the compression system than we do at full load. So I'm more excited about that than full load numbers. And then to make it a little more complicated for the chart, we have 2 part load things represented here. One of them is without the staged air volume that we're talking about, and the other one is with the staged air volume that we're talking about right now. So if I look at the code minimum unit, right, here's his efficiency for this particular example. I don't remember which code this was. Let's say it's the 2012 for argument's sake. Here's his efficiency for whatever size unit this was, and it was 11 IER. Right? If I take that 11 IER unit and I add staged air volume to it, it becomes a 12.5 IER unit. It actually gets another rating. The manufacturer is rating it without the variable speed or without the 2-stage fan and with the 2-stage fan. There's literally 2 ratings listed in the AHRI directory, one with the fan, one without the fan. And you can see I can get more efficient that way. So I can get more efficient by going from code minimum to mid-tier product, which means this green bar over to this green bar, or I could go from code minimum up to staged air volume code minimum unit. Code minimum meaning code minimum cooling design. And in many applications, many scenarios, if I do that, this unit here in red might be enough to comply with the code that is in these states. Right? So where I live in Illinois, there's a lot of times I could take what would have been an otherwise non-code compliant unit, have the manufacturer build it with staged air volume, and now it becomes a code compliant unit. Now, if I do it in the field afterwards, then I'm not code compliant still because I don't get a new rating for it. It's got to be a manufactured thing for me to get a different rating for it, right? So on an existing unit, this wouldn't matter, but on an existing unit, I'm not trying to comply with code. Only on a new install unit am I trying to comply with code. And then if you look all the way over here at the high efficiency tier, and by the way, I can do the same thing with the mid efficiency. I can get a mid efficiency refrigeration system and add the staged air volume and get even more efficient. Right? I don't get as big of a leap sometimes as I did over here because this guy was pretty much a dog. So putting the better fan in helped me a lot percentage wise. But over here it still helped, but it didn't help as much. When I go to this high efficiency, at least for the manufacturer that I chose here, they don't even have one without staged air volume. Because if you're buying the Mercedes version of this unit, you want all the cool stuff, right? So you're not going to buy it with a crappy fan. So they don't even build it that way. They only build it high efficiency cooling and high efficiency fan system. So we're way over here in this example. It was just shy of 19 IER for this particular model. I'm going to skip this because this example was just a nationwide example for Tennessee as the kind of the middle of the country, but none of us on the call care about Tennessee, so I'm going to skip that. Instead, I'm going to show you an example specifically for Boston. So this is the same software tool that I was using last week. It's called Carrier Commercial Invest, where you can do some quick calculations, quick meaning 5 minutes because I'm lazy, calculations on whether a certain technology might be worth presenting to an end user or not. And then if you want to do deeper energy modeling on the whole building, that's fine, right? So we put in some basic information over here, like weather data, what kind of application is it, office in this case, and what size building is it, 10 tons, right? And then in this case, I have 2 columns here. I have a 2015 code compliant unit, which by the way is the exact same IER and EER requirements as the 2018, which is why I didn't bother doing an update on all of my screenshots on all the software, because the table for equipment efficiency didn't change. We went from the 15 to the 18 code. Other stuff changed, but the efficiency of the DX systems did not. So there's a current code compliant unit. I selected a model that I knew complied. And then I took that exact same model unit with everything being absolutely identical on it, and I told it that I have a 2-speed fan instead of a 1-speed fan. All right, and then I calculated that. And in this case, that one thing just going from that better fan, that one thing was a 32% savings, saving me about $1,000 on this 10-ton unit a year. If you recall before, when we did things like we went from a unit and we added an economizer, it was like 5 or 6% more savings. We added DCV, it was another single-digit bump in energy savings, right? In this case, I already got an economizer on here because that's code required anyway, and I just bumped up the fan and I got a dramatic increase in the efficiency. The savings for the fan is dollar-wise is significantly more than going from a low efficiency unit to a mid efficiency and adding an economizer and adding a CO2. If I do all three of those things, it's still not the 32% that I get by putting in the 2-speed fan. 2-speed fan is by far the most dominant thing I could do to save energy on here. Well, I shouldn't say that. A programmable stat is the most dominant thing I could do. Because if I stop operating 24/7, I start operating only 10 hours a day, that saves a lot of energy really quick. But beyond a programmable stat, staged air volume is the most dramatic thing I could possibly do here. Before I continue, actually, let me finish this slide and then I'll look at the questions. So the other thing that this software was doing for me was breaking down where the savings was coming from. So in this case, $1,150 was coming from the fan savings. I had a slight penalty on cooling by changing the fan. Like, that's just a weird anomaly. $7 in the grand scheme of $1,000 is kind of irrelevant. And then I had a $120, $130 penalty on the heating side by slowing the fan down. And that one seems a little bit like, well, that's a tangible amount, 120, 130 bucks. That reason that the heating cost me more is because before, when I had the fan always operating at maximum airflow all day, it had a certain amount of waste heat associated with that motor. And the motor's in the airstream. So it's providing me heat into the airstream. When I slow the fan down, it has less waste heat. So less heat going into the duct. So somewhere along the line, my natural gas had to run to make up that difference for me to provide me extra heat. But I will gladly, quote unquote, waste $127 of gas to save $1,100 of electricity. It's a good trade-off. I'll do that every single time. So it will cost me slightly more gas usage by slowing the fan down in the wintertime. Not in the wintertime, but in the ventilation. Yeah, in the wintertime. In the ventilation hours of the wintertime, I will be getting that less heat. And then when I go into the heat, the fan speeds up anyway. But I do have to have more gas to make up for the BTUs I didn't get during the ventilation hours, if that makes sense. All right, let me expand my screen because Reddy's comment is long. I noticed a VSD requirement that a minimum 3% series reactor is recommended on the drive AC input. I see that Massachusetts prescription application for drives. I don't know what that requirement is or who's giving it to you, or what the reactor is that you're talking about. I'm not familiar with those components, but I'm also not someone who tears apart the inside of a VFD. I stick more on the control side of the equation, so I'm not sure what that particular thing is. There are times that you're going to have VFDs where you want to put things like chokes on there, right? Like ferret cores on the VFD, those black circular things, to reduce the amount of interference you could have on a VFD. Because if you have power quality issues, or if you have other things in the building that are causing some electrical, some EMF type interference, a VFD versus just a plain standard inductive motor, a VFD has electronic components in it, which could be susceptible to those things. So a lot of times the manufacturer of the VFD will put chokes on there to filter out some of that interference. That might be the reactor thing that you're talking about. Jim's saying he's referring to harmonics. Yep, so I would use the ferret cores for that kind of thing as well. In the case of these manufactured packaged small tonnage rooftop units, you're not going to get any choices at all whatsoever on what you want the VFD to be. The manufacturer is going to have a checkbox when the unit gets ordered. Do you want a VFD controlled stage air volume? Yes or no? That's it. You're not going to be able to pick any options on the VFD. It's not like we have on large chillers or like we have on a custom air handler where we can pick whatever VFD we want from any manufacturer we want with any features we want. It's not going to be like that. It's going to be a little small VFD, literally this big. It's going to come with the rooftop unit, and that's it. You either take it or you don't. There's not going to be any options. So you can spend time thinking about what you might want to do as far as like, speccing it out, but it doesn't matter because no one's going to be able to comply with your spec. It's either going to be, you're either going to get it or you're not going to get it. If you're retrofitting the VFD, like if an existing unit, it's 5 years old, you want to add stuff to it, then you have some choices, obviously, because you can retrofit whatever you want. But if you're going to buy a VFD factory installed in the unit, you don't have any choices. And then things could get more complicated if I have more than 2 stages of control. I typically don't. 2 stages is by far the most common for these mid-sized rooftop units. But you can find ones that have 3 stages of control, in which case I'm going to want to try to find ways to have more than 2 fan speeds. That's going to be fairly limiting, and I'm going to have to do some special controls to make that happen. And that will also, quote unquote, special controls are what we can also do to appease Mike's request to have a lower CFM for heating as well. But on a typical system, I'm only going to get 2 fan speeds. What is this going to look like when I want to do this? Whether I'm doing it at the factory manufacturing level or whether I'm doing it at the field installed level, the components are going to be the same. So I could have a DDC controlled system, which is not super common for this size units, but I could have that. But I'm going to stick with a traditional thermostat controlled system, because that's going to be the most common thing. So I got my thermostat over here. It could be a regular stat, a programmable stat, a smart stat, whatever it is. It has the ability to ask for 1 or 2 stages of cooling, the ability to ask for the fan to be on, the ability to ask for heating to come on, etc. So that stat wires into the rooftops control board like normal. I have a fan over here on the right like normal. And then I'm going to add 2 components in the middle. That's it, 2 components. I'm going to add the VFD, obviously. And then I'm going to add some extra relays. Specifically, I'm going to add 4 extra relays. In this case, they're all on a relay board. It could be 4 individual relays too. That's fine. But I'm going to add that. And those relays are going to be intercepting the signals from the thermostat. So the thermostat calls for Y1 for cooling. And that Y1 takes its normal pathway to go to the contactor to turn on the compressor, just like normal. But then in parallel to that, Y1 also comes into this first relay on the relay board. And then that relay goes over to the VFD and tells it that I want a low speed. And then this guy's going to send out his Y2 second stage cooling call. And it goes on and turns on compressor 2 just like normal. And then this relay board intercepts Y2 and says, oh, you've asked for second stage cooling. You must want high fan speed. And it sends that over to the VFD. And then we do the same thing on the fan call G and the heat call W. So these 4 relays are intercepting the signals from the thermostat that go to the things that they need to go to, compressor, gas valve, etc. It's intercepting those and relaying that same information to the VFD so he knows if he should go into low fan speed or into high fan speed. The other component of this is going to be the economizer. The economizer we talked about last week, that's my free cooling device, right? So I'm going to have that. That's great. Anybody spending money on staged air volume to save energy is probably also going to be spending money on an economizer to save energy. The economizer controller I'm showing here is a Honeywell Jade economizer, 7220. It is by far the most common current economizer. If I have older Honeywell economizers, I can't do any of the staged air volume stuff with them at all. They're out. This is the only one that would work. I could also use a Belimo Zip economizer controller, or I can get one from like Johnson or somebody else. If you get like their current model of economizer control and you choose the code compliant one, it's going to be able to do the things we want it to do here. So that's the one I'm choosing because it's well more than 50% of the installs get this guy. So here's what's going to happen with the economizer when we do this staged air volume. And this is hopefully going to make things helpful for Mike's question that he asked us earlier, which was a great question, and I did not explain well. This is going to help us explain it well. So here's my rooftop unit. I got my return air coming up here from the building in orange, going into the system, going through the filter and the cooling coil and the fan, and then into the supply duct, and I'm running at 100% airflow in this case. So for this particular fake job, I have 4,000. It's a 10-sun system with a traditional nominal 4,000 CFM right now. Okay, I have 4,000 CFM coming down the duct. In this particular example, they needed 800 CFM for ventilation. So through this opening and through the blue dampers, I'm going to bring 800 CFM of ventilation. And then my return air coming back, my 4,000 CFM, 800 of it is going to exit out the exhaust path that way, right? And then 3,200 is going to go through the red dampers this way, and my 3,200 and my 800 combine to give me my 4,000, which is what I'm delivering to the building. This is my normal scenario here at my full fan speed, right? So 800 comes that way, which means 800 exhausts down over here, right? Now when I slow the blower down, let's assume I don't change the ventilation position of the dampers. I slow the blower down to that 1/3 reduction, so 67% blower speed. Now my supplier is not doing 4,000, it's doing 2,700. And through this opening, I don't have 800 sucking in anymore. I only have 500 sucking in. Right? I lower the fan speed, I'm obviously going to move less air. Well, 500 doesn't comply with my code. My code says I need 800. Just because I asked for less cooling doesn't mean I have less people to ventilate for. It might mean that some moments, but in general, it does not mean that. So I now 300 CFM short on my ventilation air. So whenever we go to the low fan speed, somebody's got to tell the economizer damper, hey, don't use that minimum position. Use a bigger minimum position. I need you to go up to this other position so I continue to get 800. So I need to have dual minimum positions on the economizer controller, right? So that's why I'm using this Jade controller, because it can handle that. And as that thermostat is having these relays go through here to the VFD, those same Y1 and Y2 calls, first and second stage cooling, as well as the heat call, are going to go into the economizer controller. So he knows the same thing that the VFD knows, which is the same thing that the compressors and the gas valve know. Everybody knows that I have Y1 for cooling right now, or I have Y2 for cooling second stage, or I have W for heat. All the pieces know by intercepting those signals. So regular scenario, I have full airflow. I got my 800 CFM. When I go down to the reduced speed, I have to open up my blue dampers a little bit more. My little animation opens them up because it's so creative. Opens them up a little bit more to continue to get the code minimum air. Now, if I wanted to do a third airflow for my heating, right? So I don't want to do the 67% or the 100. I want to do, let's say, 81% for my heating. I determine that's the lowest amount of CFM that I could put through my particular unit and keep the heater online without hitting high limit. If I want to do that, then I need to get a different kind of economizer controller that has 3 minimum damper positions. The problem is none of the packaged controllers, meaning Honeywell, Belimo, those kind of things, none of those things have more than 2 minimum positions. They don't make one that has 3, which is why I'm limited to only having 2 airflow speeds right now. As soon as somebody manufactures one with 3, now I can have 3 airflow speeds, but nobody does that yet. Now, if I really want to do it, that's fine. I can do it without this Honeywell controller or Belimo controller, and instead do it with a building automation system, meaning I have a DDC intelligent board here that can program however I want, and he doesn't have an economizer controller at all. He has the economizer functions built into him, and he has an output that tells the damper what to do. Well, I could just program it in here to have 2, 3, 4 minimum damper positions if I want. So with a building automation system, I could have more minimum damper positions. Hence, I could set things up to have more airflow speeds if I wanted to. But with a regular, traditional, non-DDC system, I'm going to be pretty limited, and it's 2 speeds only if I want to comply with the ventilation code. So hopefully, Mike, Mike typed in, okay, that makes sense now. I was doing a bad job explaining it before, and I was just like, Mike, just wait till we get to the slide with the drawing, and it'll be easier to get. All right, so hopefully we're all good on that now. I know it kind of sucks that we don't get that 3rd speed for the heating reduction, but I mean, and I'd like us to get to that point, but I'm still pretty happy and excited that we can at least get to the 2-speed scenario, because like you just saw, it's saving somebody $1,000 on their 10-ton rooftop in Boston. So it's still a giant savings. If I can save them $1,200 instead of $1,000, that's a better story. But at least getting that $1,000, because most of the savings is coming off the fan hours, because the fan only hours are way more than the heating and cooling hours. So that's where the savings is coming from. I'm not going to get a giant, humongous leap by doing it on the heating side. It'll help, but it won't be giant, humongous. All right, so if you want to do staged air volume, you have 2 ways you can do it. You can buy a brand new rooftop unit that has this built in, and that's fairly common now because it's code required in a lot of states. And even if you're in a state where it's not code required, you could still buy it. You could just say, hey, I want one that's code compliant in Massachusetts and ship it to me in Maine. Or you could do that if you wanted to. I could buy it that way, or I can retrofit my existing unit. So I'm showing 3 here. There's probably more than 3 nowadays, but I'm showing you those 3 brands from that Pacific Northwest National Lab study, the Catalyst, the Enerfit, and the Digi. Those 3 guys can definitely do this. And what you do is you give them the model and serial number of your equipment, right? And then they send you out a box that has everything you need, all the sensors that you need, all the relays that you need, the little VFD down here that you need, and a box to put all the control stuff in. What they are sending you is a DDC control. right? It is more elaborate than the simple stuff I was just showing you a minute ago. It is a DDC control, so you could get more than 2 minimum positions that way through their types of system. Now, should I get a new rooftop with staged air volume, or should I retrofit my new unit? Well, that's a discussion that takes us back to last week on whether I want to replace my unit or repair it. Well, in this case, instead of replace versus repair, my debate is replace my unit or enhance my unit. But it's going to be the same exact process. I'm going to go through and evaluate my equipment. I'm going to use that scorecard type of thing that we had before. If you don't remember what I'm talking about, the scorecard, or if you're new, go back and watch last week's video and we'll talk about that scorecard. And all those questions would be the same on repair versus replace, except where it said cost of replacement, take that out and insert cost of enhancement, and then do the same exact scorecard and decide what you want to do based on that. As a general statement, what I'm going to tell you is if you have a rooftop unit that's, 10, 12 years old, it's not worth investing money into enhancing it, because if you recall, the average life expectancy of your rooftop is only 15 years. I don't want to put $4,000 into my rooftop unit of enhancements that may only last me a few years. Now, can you make your unit last till it's 20, 25 years old? Yeah, sure you can, by doing all the right things and all the right maintenance. But generally, when I get above 10 years old, I probably don't want to spend money making my unit better, right? But if I'm at the point I might want to replace it, right, I'm going to buy a new rooftop anyway, and I'm already going to spend whatever, $9,000 to buy the new rooftop unit. Why not spend $10,000 and get the new unit that has the staged air volume in it, or whatever the extra price adder is, right? So it's kind of like, I don't know if I gave this example last week or not, but like windows. If anybody's ever bought new windows, it's like $30,000 to do your whole house, right? And that's a big giant investment. And then you're looking at the energy savings and you're like, oh, it's only going to save me like $400 a year on my gas and heat bill. It's going to be a forever payback, right? So I'm not going to do it. I'm not going to buy new windows just to save energy. I might do it for other reasons because they're ugly or whatever it is. But when my kid throws a baseball through one of the windows, and now I'm buying a window anyway, it's not that big of a deal, right? If I have 30 windows and each one's $1,000, so that's when I had $30,000, so $1,000 for the window, right? Well, maybe I buy the cheap window for $900, but the energy efficient one is $1,000. Well, now the price differential is not that big of a deal. I'm paying for the upgrade because I got to buy a window anyway. I'm already paying $900. Just spend $1,000 and get the better window. But my choices are spending $0 and getting the good window. That's dramatic. Same thing happens here. When you're going to buy a new rooftop anyway, don't try to figure out the payback on the whole entire rooftop unit, because it's going to be a decade, right? Look at the payback on the upgrade. How much extra does it cost me to get the better rooftop versus the entry-level rooftop? Because I already got to buy the entry-level rooftop because I need a new one either way. So how much more does it cost me for the upgrade? And then what's the payback on the upgrade is the way I'd want you to look at it. And there might be more manufacturers now. When I made this slide a couple years ago, these are the ones that had it. But honestly, that's like 90% of the mid-size rooftop manufacturers. So I don't know who I'm missing. I guess I'm missing American Standard, but I probably could just put Trane/American Standard. But after that, that's pretty much the market. Those are the people that make these things. I guess I could put Daikin/McQuay/Goodman. Those are all made. So these are the people that are making units. They might have other brands they use, but these are pretty much all the manufacturers. And then the other thing on here is I have this one that says make your own kit, right? And I did that for a very specific reason, because these kits are really expensive. No offense to those dudes. They're doing all kinds of cool stuff, but it's thousands of dollars. And then I still got to have the labor install it. And it makes it really unattractive for a small unit. You got a 30-ton unit that's like 4 or 5 years old. This might be a good way to go. But I got a small unit, 5, 6, 7, 10 tons, right? It's going to be hard to get a payback out of that stuff. So I made up this kit years ago to do this exact same thing. And it looks like a bunch of stuff, because it is a bunch of stuff. But it gets real simple real quick, because the first things on this list: economizer controller, actuator, these sensors, the CO2, the thermostat stuff, all of that I am going to buy anyway just to do an economizer. If I want to retrofit an economizer in my unit, I'm buying all that stuff. The only things extra that I'm buying are the two last items, the VFD. In this particular example, I picked a very specific one for a specific model of unit. It was a 3 horsepower, 480 volt VFD from Honeywell in this case. But I could get one from anywhere. And obviously the horsepower and voltage depends on your project, right? And then I was getting 4 relays. Those 4 relays were the same thing that the manufacturer gives me with this relay board. But I was just getting 4 plain relays. I didn't have them on a little board all buddied up. It was just 4 relays, right? So that's the things that I would buy to make my own kit. Like I said, you're buying all this stuff on top right here anyway to do an economizer with DCV. you're probably buying a thermostat anyway. You may or may not want to get it on the internet, and you may or may not want the Honeywell stat. You may want to do something else. That's fine too. So I take all this stuff, right? And the reason I use the Honeywell stats is because they were already on this wiring diagram, right? So I take all this stuff, and here's the wiring diagram, which also looks like a lot of stuff. But I'm already putting the economizer controller in. I'm already buying all these sensors to put on it. I'm already wiring all this to the thermostat. The only extra thing I'm wiring is these 4 relays and wiring them down to the VFD. And if you follow the wiring for these relays, which I don't expect you to do on the tiny screen right now, all they're doing is they're intercepting the fan signal from the stat. They're intercepting the cooling signal from the stat. They're intercepting the second stage cooling signal, and they're intercepting the heating signal from the stat. Those signals are still going to their normal places, economizer, gas valve board, etc. But I'm intercepting them, and I'm also running them over to my VFD. All right, does that make sense? Anybody have questions on that? All right, I'm going to squeeze in a little topic before our break here. I was debating whether I'd have time or not, so I didn't put it on the agenda, but I'm going to squeeze it in. Because usually somebody asks, nobody did this time, but usually somebody asks, hey, one of those retrofit kits, they were doing compressor speed control in addition to fan speed control. Like, how do I control compressor speed? So let's just take a little 7-8 minute detour on compressor capacity control. Just so everybody's on the same page with that before we move on to our next topic. So the way I like to explain the need for compressor capacity control is by explaining cooking on a stove with a burner, which sounds stupid. Like, why using heat to explain cooling? I don't know. It's just an example that I got. So if I am sitting there cooking dinner for my family, let's say I'm going to make spaghetti, right? When I make spaghetti, I boil pasta and I heat up sauce in the microwave because I'm lazy, and I throw it on the table and I say, let's go, kids, time to eat. My wife makes it. It's totally different, right? She's got the pasta. She's got the sauce. She has vegetables. I don't know why we need that, right? Going on. She has all these extra things going on. So when she's cooking the pasta, she has all the burners going and all the pots going. I have a big family, which is why we have these giant pots. No, I'm just kidding. This isn't my stove. I just Googled the picture. So she has all the burners going and all the pots. But when I'm going, I only have 1 pot. So I only put on 1 burner. There's no reason for me to put on 4 burners if I only need 1 pot of water to boil. I'm not making the broccoli. I'm not boiling that or whatever. Right? I'm not making the other stuff. Just got the pot. Right? That's it. So I only put on 1 burner. The same logic's going to apply with our cooling systems. If I only need 1 unit of capacity, only turn on 1 compressor or 1 stage. Why are you turning the whole thing on? Same thing applies with my car, right? With the teenage example. If I only need to get my car up to 35 miles an hour to go from this stoplight to the next stoplight, there's no reason to jam my foot all the way down on the floor with the gas pedal and go full bore. I don't need to do that. Why can't I just use a little bit of capacity control, i.e. my foot in this case, to edge off it a little bit? So that's the logic we're going to take with the compressor. Only use the capacity you need. Don't turn everything on. Only turn as much as you need on. It sounds kind of like obvious, but historically most systems only have 1 stage of cooling, especially small systems, and it's just on or off. Or maybe they have 2 stages, and it's just stage 1 on, 5 tons. Stage 2 on, 10 tons. That's it. Nothing in between. So we're going to try to find ways to get that in between. If I look at some of the graphs we looked at last week, right? This was a graph we showed you for Boston, and it showed you all the different quantity of hours I spend at various 5-degree temperature bands, right? So at 60 degrees, I'm spending almost 1,000 hours of the year. And if you didn't know, there's 8,760 hours in the year. So I'm spending, 1/10 of my year at 60 to 65 degrees, right? I'm spending 500 hours a year at 50 to 55 degrees, et cetera, et cetera. Well, I'm designing my system for a 90-degree day outside. That's what I'm designing my cooling system for. But I spend very little hours on a 30-year rolling average at 90 degrees. I mean, there's hours there. It happens, right? And there's also a day where it's going to be 98 in Boston. That happens. But it's not my normal scenario. So if I design my system for this day, whenever I'm at these other days, I have too much capacity. So I either need to turn things on, off, which, by the way, beats the hell out of things, right? Just like the 17-year-old driving the car. Or I need to see something that can go up a little bit. Hey, let's turn it on 20%. Let's turn it on 50%. Let's turn it on 80%. Let's turn it on 100%. I need something I can stage up. So these days where it's mild, I don't need as much capacity. I can stage it down. So let's talk about the different ways I could stage this or modulate it, depending on what we're going to look at here. So the first thing is just on off. 1 compressor with 1 speed. You turn it on, you turn it off. If you want less cooling, you just turn it off longer. When you want more cooling, you turn it on more. more time, right? That gets me the goal of getting the BTUs, the cooling capacity that I want, but I'm not getting it in a very uniform fashion, which means I have cold air coming out of the duct, then warm air, cold air, warm air, cold air, warm air. It also does a really, 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 really bad job dehumidifying. In order to dehumidify a space, I need your compressor running 7, 8, 9, 10 minutes at a crack. And if I'm turning it on for 3 minutes and then back off, I'm getting very little dehumidification time. So on off is the absolute worst thing you could possibly do, but it is what most systems have. The next thing would be do is give you 2 compressors. Turn one on, turn the other one on. So if I have a 10-ton unit as my example, I turn on one compressor for 5 tons. I turn on the other 5-ton compressor for a total of 10 tons. That's much better than just on off. It's not awesome, but it's better. The other thing I could do is get 2 compressors like I'm showing in the drawing down here, but get ones that are not equally sized. So let's just pretend I still have a 10-ton example. And let's say that this guy is a 4-ton compressor and this guy's a 6-ton compressor. So I can use 2 compressors to get 3 stages. I could turn him on to get 4 tons. And then when I want more cooling, I turn him off and turn on his brother for 6 tons. And then when I want even more cooling, I turn both of them on for a combined 10 tons. So I have 4 tons, 6 tons, 10 tons. So I have more steps there. I'm not buying more compressors. I'm just controlling them smarter by not having them be equal sized. Historically, you would get 2 equal sized compressors. Doing 2 unequal sized compressors is a more modern idea. In some larger buildings, they don't like this. They like to have, they have 20 rooftop units. They're all the exact same model, and they all have 2 compressors, and they're all the exact same compressors. So they keep one spare compressor down in the shop. And if I don't ever fails, they always have one. They like that idea for a spare parts concept. But honestly, on stuff that's this small, compressors are readily stocked at local distributors, so it's not a problem. If you had some really special niche thing, and it was some giant, huge compressor at some critical facility like a data center or a hospital, okay, I got you there. It makes sense. But at a normal office building, you could seriously wait 4 hours for me to drive over to the supply house and get the compressor. You could wait. It wouldn't be the end of the world. So having this staging thing kind of works out. The more stages, the better the humidity control, the lower the energy consumption will be. Those 2 things will work in my favor. All right, I'm going to show you what we can do on a reciprocating compressor. Even though nobody uses reciprocating compressors anymore, these are obsolete. Everybody's using, for the most part, on the kind of equipment we're talking about, they're using these small scroll compressors. Same thing we use residentially for the most part. Or they're using rotary. But reciprocating compressors look like this. And you will find these on a lot of existing units. Now, those units are getting long in the tooth. So at this point, I don't know how much I would invest in upgrading those systems like I'm going to talk to you about right now, because those units are probably at the end of their life anyway. But if you had some that were in great shape and they weren't quite as old, maybe they're only like 12 years old and they're still in excellent shape and you want to enhance them, maybe you would do this. So what you can do on a reciprocating compressor is you can add an unloader to it. I cannot do that on these scroll compressors. There's no way for me to retrofit an unloading device on here. But these reciprocating ones I can. So this is kind of stupid, but I'm going to draw it like this. I'm going to draw 6 heads on one compressor. So I got this one compressor that has 6 heads. Think of this like, for right now, think of this like as a V6 engine in your car, right? I got this piston and that piston. They're kind of like opposites of each other. They're yin-yangs, right? Kind of got the same kind of idea going on here for the most part. So I have 6 heads on this compressor, and what I can do is I can add unloaders to 2 pairs of those. What unloaders do is what the name sounds, is I unload them when I don't want them. So when I want maximum cooling, I just run the compressor and that's it. When I want less than maximum cooling, I could unload this bank, and now I'm operating at 67% of capacity. Then I could unload this bank and I'm operating at 1/3 capacity. So with one compressor, with unloaders on 2 parts of it, I can get 1, 2, or 3 stages. And a lot of times if I have a reciprocating compressor, I have 2 of these things, right? So I have another one over here, right? And now I can get 6 stages by adding 2 unloaders. I don't even have to add unloaders over here on the left side at all. I don't need to do that. So for stage 1, just run this guy. For stage 2, run this guy and that guy. For stage 3, run everybody over here on the right. When I want stage 4, what I would do is turn this guy on for all 3 of its pieces, turn number 3 and number 2 back off. So I got these 3 over here, plus the bottom guy over here. That's my 4 stages. And then I can go to stage 5 and stage 6. So if I'm smart with my controls, my sequencing, I could do 2 unloaders on these 6 banks and get 6 stages that way by only buying 2 unloaders, which is kind of cool. I do want to point out pressure unloaders versus electric unloaders. Pressure unloaders unload based on pressure. They have sensors that monitor the refrigerant pressure, and when the load in the space changes, that causes the pressure to change, and we can stage the compressor off based on that. Electric unloaders use a microprocessor control to look at something else other than pressure. So in a large VAV system, like we had mentioned previously, they would look at duct temperature sensors, right? On a constant volume system, they would look at space temperature sensors. And when that room doesn't need as much cooling, we would unload based on that. Electric unloaders are a very fast way to do it. Pressure unloaders take a little bit of time for the pressure to react. If you're going to retrofit on a VAV system, which is not the main subject we have today, but I've mentioned it several times, but if you're retrofit on a VAV system, it has to be done with electric unloaders. It cannot be done with pressure unloaders. They're not fast enough to react to this change in supply air temperature that I need to babysit. I'm trying to maintain 55-degree supply air in the duct. I have to do that with the microprocessor, and therefore I have to do the electric unloaders. Right? Pressure unloaders are fine for constant volume systems like we're talking about today. All right. The next thing I could do on systems would be to put high gas bypass in. This can be used with those scroll-based compressors that I had shown you before. It could also be used with the reciprocating ones, but it's not necessary, right? And it can be used with actually anything, centrifugal compressors, rotary compressors, screw compressors, they all could do it. So hot gas bypass, the way that works, and I know there's a lot going on here, and I know you guys aren't super familiar with the refrigeration cycle, but actually in the heat pump section, we will go through the refrigeration cycle today, so it might become more obvious. I probably should have did the heat pumps first, I guess, and did this last, but too late, we're already in. So here's the quickie version of the refrigeration cycle. I have this evaporator coil in my airstream for my interior air in the building. His job in life is to absorb heat from the indoor air. And then he absorbs that into his coil, puts the heat into the refrigerant piping, and sends that out to the compressor. The compressor increases the pressure, which increases the temperature. Then I send that high temperature refrigerant to my condenser coil outside, where now it's hotter than the outdoor air, so it can dump the heat to the outdoor air. And then it comes back in, goes to the TXV or other metering device to lower the pressure, which lowers the temperature, and now makes a cold refrigerant in the evaporator again to absorb energy. And that cycle keeps repeating. And I'll go through that in more detail in the heat pump section. What happens when you put hot gas bypass on there is you grab off of the compressor some of that hot gas and you don't send it to your condenser coil outside. Instead, you send it and shove it right back into your evaporator inside. You add a bunch of heat to the indoor side of the unit, which causes this unit not to give you as much cooling, which causes this compressor to have to run longer cycles to stay online and cool the space. So I'm getting my capacity control not by being smart and turning off compressors or turning off parts of compressors, but by falsely loading my system just to make my compressor run a really long time. It does a really good job of controlling my humidity and making my space be in check and giving me tighter temperature control, but it's super inefficient. Anytime you hear the word bypass, that just screams inefficiency on anything. I'm going to bypass doing it the right way, and I'm going to do it this way, right? It works, and you can get it done. Sometimes what we'll do is on machines that have these scroll compressors, especially big machines, I might have 4 scroll compressors, and it's still not enough staging, so I'll put hot gas bypass on the first compressor to give me like an extra bonus stage. I don't have to use it very often, but every once in a while it might kick in. So you can get this factory installed on some equipment. You can also do it as a field installed thing. If you're going to do a field installed thing, you're probably going to do it with a device called a RAL device. That's a specific brand and manufacturer. I don't represent them. I don't work for them. I don't even know anybody that's there. But they make a version of this hot gas bypass, and they do it a little bit smarter than the way that I described, but it's still pretty much an energy pig compared to doing nothing. It's more efficient than the field way that guys used to do it, but it's still the least efficient way that you could control capacity of a system. But we use it as a retrofit when something's wrong. Like, hey Ryan, I messed up and I oversized this equipment and now it's too big and it's all this humidity problems. And oh, by the way, it's a fitness center and it's just nasty in there. What can I do? And I'll be like, well, you can resize your system and put a new unit in. No, I'm not going to do that. What are my other options? Well, I guess you could retrofit a raw device. Yeah, I like that idea. It's only going to cost $1,000 instead of $10,000. I like that idea. Okay, do it that way. That's when that will come up. No offense to the raw guys. All right, the next thing that you could do, Riza asks, how do you sequence the compressor with the fan speed? Right now, what we're talking about is just multi-stage compression, like two-stage compression. If I just have 2 stages, for example, I will just have 2 fan speeds. And the way I'll sequence that is exactly the way we were doing it over here, right? With this fan speed control, intercept the signals from the relay. As he's telling it to go to stage 1 or stage 2 of compression, I'm going to stage 1 or stage 2 of fan speed. That's how we're going to do that. If I was to have something with more than 2 or 3 stages like that, and I was doing like this with 6 stages, then I would have to have fan speed control, something more than what we've talked about today. Probably VAV systems would be what we're doing in this case, right? Or I'd have to just keep the higher fan speed, which doesn't do as great of a job dehumidifying, but I can still do it that way. And historically, it's been done that way. If I go to what's called a digital scroll, one specific manufacturer of compressor makes that, Copeland. Once again, I don't work for Copeland. I don't rep them. I don't get spiffs for selling their stuff. But they make this thing called the digital scroll. I probably should have done this. I should have hunted a video down. But I didn't do that. So instead of a video, you'll get a crappy drawing from me. All right, in the top of this compressor, if you were to cut it open, let me get something to draw with. That's not going to do it. Inside the top, you're going to see a scroll like this. All right. And then in the bottom piece, there's going to be another scroll that's like the opposite of it, and he's inside him. Right? So I have this one up on top and this one on bottom, and they go together. And as that top scroll turns, it's rotating like that, the refrigerant comes into the sides, and as it gets spun through there, as it's rotating, the diameter of the opening gets smaller and smaller and smaller and smaller. And that's going to compress the refrigerant. That's how a scroll compressor would work. The top guy is rotating, and it's just taking that refrigerant from the outside and just moving it closer and closer and closer and closer and closer to the middle until there's nowhere left to go, and then it ejects out the top and goes into the condenser coil. What's going to happen on a digital scroll is the same thing. That top head is rotating with the bottom piece, but what it's going to have the ability to do is to physically separate those two. So I'm down here, I'm doing work, I'm compressing refrigerant. When I separate them, even though that scroll is still turning, it's not doing any work. It's not compressing any refrigerant. All the refrigerant is just flowing straight through because there's no touching of the 2 scroll pieces of metal. When I put them back together, then I'm doing the work and compressing refrigerant, and then I'm not, and then I am, then I'm not, then I am, then I'm not. And that's how this digital scroll works. It loads, unloads, loads, unloads, loads, unloads. That's what it's going to do. And the pace at which it keeps those things together depends on the amount of capacity that I want at that moment. If I want full capacity, they stay together the whole time. If I want half capacity, they separate for 3 seconds, go together for 3, separate for 3, go together for 3, separate for 3, go together for 3, right? If I want 75% capacity, they stay together for, 3 seconds, and then they separate for 1, and then they're back together for 3 and separate for 1. And we're going to pulse them together to get the amount of capacity that I want. It's a fairly effective way to control the capacity. The only real negative to it is it tends to be loud. There's annoying sound that it makes when it does this. So you would never do this at like someone's house, right? And you probably don't want to do it at a school in a residential neighborhood because now the people in the house next door are going to hear this. But on top of the roof of a commercial building, it's not like you're hanging out on the roof. I mean, if you have a roof garden, don't do this, right? But normally, who cares? Nobody's going to hear it anyway. So if it's going, you probably like my sound effects. They're excellent, I'm sure. Right? If it's making that kind of annoying noise, there's nobody there to hear it, right? So if a tree falls in the woods and nobody's there to hear it, it doesn't make a sound. I don't know if it makes a sound. I don't care because I'm not there, right? That whole logic. So this is going to be significantly more efficient than hot gas bypass by far. Hot gas bypass uses more energy than if I did nothing. If I did nothing, I just turned my compressor on and off, that's more efficient than the hot gas bypass I was telling you about before. Because hot gas bypass just keeps running the compressor constantly, or at least long cycles. This is going to be more efficient than that. It's going to be significantly more efficient than the hot gas bypass. It's a much better way to do it. Other than the sound, the only other real knock is there's really not any good way to retrofit this. No one's going to give you some kind of like piping diagram and control sequence on how to retrofit this onto your existing unit. That doesn't exist. It's available from a lot of manufacturers as a factory installed thing, but as a retrofit, not really realistic. The last thing we have for capacity control is we can go to an inverter, right? This is just another VFD, like the VFD we were putting on the fan. Now I'm putting one on the compressor, right? And I mentioned that one manufacturer, Digi, was doing that very kind of thing. Some of the equipment manufacturers, for example, I do a lot of work with Carrier. So now I am telling you the name of someone that I am involved with. So take this with a grain of salt. But Carrier has a rooftop unit that has a variable speed compressor and a variable speed fan, and then it sequences those two things together to get tighter and tighter capacity control. Because of that, they also have to modulate the minimum damper position, so they can't use a standard economizer controller. They have to use more of a programmed one, right? Not a standard off-the-shelf Jade. But in any case, I could put an inverter on the compressor, and this has been done for decades, mainly on chillers. Remember before I said, by the time packaged rooftops get something, it's either technology that's been brought up from the residential world and adapted, i.e. staged fan control, or it's cool stuff from the chiller guys that's been brought down, in this case, i.e. Compressor control. Although with that being said, we've been doing it for decades on chiller compressors. We've been doing it residentially for 10 years as well. I have one of the units in my lab. It is now year 10 of me having a residential inverter-driven compressor in my lab. When I say lab, I don't mean testing lab. I mean training lab for teaching techs how to do it. So we've had 10 years of having inverters on regular residential split systems. And if you look at the ductless mini split guys, they've had it even longer. So this is not novel at all. At my house, I've had an inverter, I'll say 4 years now I've had an inverter at my house. Mine's a little bit limited, if you will. Instead of fully modulating, which is hard to control, it has 5 specific capacity points, 5 stages. But it's nice. 5 stages is awesome. It's not as good as infinite staging, but it's pretty awesome. I get excellent humidity control. But I can retrofit. Actually, this inverter on the left is the exact inverter I have at my house. But I could retrofit these inverters. But the problem with retrofitting them, it's a lot easier to retrofit. You can't retrofit a digital scroll. You can, but the whole compressor's got to come out along with all the controls and everything. Here, you could leave the compressor in and retrofit an inverter VFD onto it. The problem is the manufacturers of the compressors and the manufacturers of the rooftops will not support that. They're like, nope, sorry, no warranty if you do that. Now, if you're already out of warranty and you don't care, right, maybe you want to do it anyway. And you certainly could do that if you want to. But it's on you to do it, not them. If the compressor dies after you put the inverter on, don't expect them to honor the 5-year compressor warranty that you thought you had, right? On a new unit where the manufacturer puts this in at the factory level, okay, well, yeah, it's obviously warranted because they designed it and built it, so they're going to back that up, obviously. Let's see. Anika asks, when controlling the compressor, what are some potential issues that can arise? Coil freezing, flooding, etc. Yes, those kind of things could arise. Once again, if you buy one that's factory designed and factory controlled this way, you have very little to worry about because somebody else has already engineered that for you. If you want to retrofit this on here, yes, you're going to have to pay attention to those kind of things. You have to have enough airflow both on the indoor fan and on the condenser fan. I should mention that too. When you do this, you're going to need a variable speed condenser fan as well as a variable speed indoor fan. You want all these things to match together. But you're going to have to make those things match together if you're retrofitting it yourself. If you're buying a factory installed package, they take care of that. For example, my house, I have a modulating indoor fan, fully variable speed indoor fan on my furnace. I have a 5-staged inverter-driven compressor, and then I have a condenser fan that matches those 5 stages. And then I have a control on my wall that babysits all of those and makes them all work together. So I don't have to do anything special in terms of how I control it. It just happens. And it's not like it's a unique thing. Like at my office, we do, I don't know, I'll make up a number for right now, say 1,500 of those residential systems per year. We do like that have those kind of controls already set up. You buy the right condensing unit with the right indoor furnace, with the right thermostat, and you just wire them together, and it automatically just does everything. The thermostat actually interrogates the model numbers of the equipment outside via a communication cable, and based on those model numbers, it already knows which speeds of everything to set up for it. It's already pre-engineered, right? And the commercial rooftops that have this kind of thing are also the same way. They have a variable speed condenser fan, variable speed compressor, variable speed indoor fan, and they come with a built-in controller that already knows which speeds of which things to pair up together. So there's not really a lot of thought process or extra engineering involved. If you're going to do this in the field, then obviously you have to engineer all this stuff because you're making it up as you go kind of thing. From a code standpoint, when you have systems that are 75,000 BTUs, which is more than 6 tons of cooling, you're required by statewide code to do 2 stages of cooling or more. You are not allowed to put in, say, a 10-ton one-stage unit. It has to be 2 stages. This is being done for energy conservation reasons. However, there's also a dramatic benefit for the humidity control that we talked about. If you happen to have a zone damper system, which is not today's subject, but if you did, then depending on how big the system is, you either need 3 stages of compression or 4. They don't care if you get it by putting in 4 little compressors. They don't care if you get it by putting in multiple unequal size compressors. They don't care if you use an inverter. They don't care if you use a digital scroll. You just have to get the capacity control when you have these different things. All right, it is 9:43 Central Time, 10:43 Eastern Time. Let's take a 10-minute break. Let's just come back at 10:55. So an 11-minute break. Get the coffee, donut, bathroom, etc., etc. All right. It is 10:55, so we are back from break. A couple things to discuss real quick here. Alberto from UMass, that's helping us organize these events here. He wants to mention and remind you guys that if you signed up properly, hopefully you did, that the CEUs are available and will be sent to you guys afterwards. If for some reason you signed up on the UMass site and got your link for GoToMeeting and signed up for that and registered, and then passed the GoToMeeting link to a coworker, they're not going to get the certificate. Only people that signed up properly to the UMass site will get the certificate. So if you need that, make sure you go back and sign up for that. Let's see. Mark had a question about affinity laws with whether in practice 3 is suitable for an RTU fan since it doesn't have VAVs, or is this an idealized rule law? The fact that there is or is not fan dampers there or zone dampers there has no effect on whether I'm going to be changing my horsepower consumption as I change my blower speed. It will be the reason why I change my blower speed, but it won't have any practical effect on it. All right, let's move into heat pumps. All right, so the reason why we're talking about heat pumps is because in many climates, including the ones that we're talking about today, heat pumps are underutilized and could be used much, much more. Right? If you're like in Florida, you already get the heat pump thing. Like you've had it for years, you know what you're doing. Like heat pumps are fine. But if you're in the Northeast or in the Midwest, heat pumps have not been maximized to their full benefit. So we want to explain how heat pumps work, how they can save energy, when you might want to use them, when you might want to not use them, and then we'll move into variable refrigerant flow heat pumps, which is just a much nicer, cooler, fancier version of heat pumps, right? All right, so let's explain how heat pumps work. In order for me to explain how heat pumps work, I'm going to have to explain how an air conditioner works. And many of you probably think I already know how it works. It makes air cold. And that's not quite true. So we're going to go through it in a little bit of detail here. So up here on top, I have your regular air conditioner. Let's just say at your house for this example. On the right-hand side is the evaporator coil in your house. That's in your fan coil, your air handler, above your furnace, whatever it is. Right? You got that guy there. Air from your house comes through. It is warmer than the refrigerant in the coil. The coil is going to be like 40-some degrees, and the air coming back to it's like 75 degrees. Heat always goes from the hot thing to the cold thing. So in this case, the hot thing is 75-degree air. It's going to give heat to the 45-degree refrigerant, thereby cooling the air down, and more importantly, or equally important, warming up the refrigerant. Right? So now I've given it the heat. My air gets cold. Now I send the warmer refrigerant to the outdoors, and I reject that heat through a coil and a fan out there. The first thing that you might be thinking is, well, Ryan just said heat always goes from hot to cold, right? It went from this hot air to this cold refrigerant. But I'm somehow going to try to take heat from your inside of your house and put it in your hot yard. That's the opposite. That's going from cool house to hot yard. How are we going to do that? We're going to do it with the refrigeration cycle. We're not going to break the hot to cold rule. We're just going to use the hot to cold rule multiple times and play a little game in between to make it work. So just know for right now, for a cooling cycle, the evaporator coil in your building or your house absorbs heat from the air and then dumps that heat into the outdoors. Now what a heat pump does is it's the opposite. But opposite doesn't mean the compressor runs backwards. It doesn't do that. Opposite means is I pick up this air handler and the evaporator coil. I literally pick them up. Imagine if I did this. I literally picked it up and I went and set it down in your yard outside. And then I grabbed your condensing unit and I picked it up and I put it in your living room. And then I turned everything on just like it was normal. It doesn't know it's in a different building or inside or outside. It doesn't know. It just turns on, right? So in that case, outside, I would be absorbing heat and moving it to the inside coil. And that's what a heat pump's going to do. It's going to switch the evaporator job and the condenser coil job. Now, it doesn't physically pick those up and move them in and out of your building because that's ridiculous. It has a reversing valve in it that flips, and it switches how things get piped. So this coil that was my evaporator coil for cooling, now when heating, that literally becomes my condenser coil. Refrigerant condenses inside it now. And then this guy that was my condenser coil in the summertime, now he becomes my evaporator coil. The refrigerant evaporates inside it instead. So now what I'm doing is grabbing heat from this air and dumping into the refrigerant, and then moving that heat to this coil. That's how my heat pump's going to work. Now we'll go in a little more detail here. So on the refrigeration cycle, I'm going to explain the refrigeration cycle by boiling water, which sounds stupid. Like you're going to use hot stuff to explain cold stuff. That doesn't make sense. So I got this pot of water. I got the flames on it here. I'm warming up the bottom of the pot of water. I'm conducting heat through the metal pot into the water. Right, the water is getting warmer and warmer. It started out as 58-degree water from the city. Now it's 70, it's 100, 120, 130, 180, 190, 200, 210, 211, 212-degree water. I'm still adding heat to this thing. If I keep adding heat when the water's at 212 degrees, the next thing that happens is not that the thermometer goes to 213. It just stays at 212. Now what I start doing is boiling the water. I use the energy from the fire to change the state of the fluid. And if you didn't know it, it takes a boatload of energy to change the state of a fluid. You know, liquid to solid, solid to liquid, liquid to gas, gas to liquid, that kind of thing. So I'm adding heat to increase the temperature. And then once I get to the boiling point, I'm still adding heat, but now I'm using the heat to convert the state of the fluid. And I obviously have steam rising out after that as well. So we can look at those two things as two different kinds of heat. Sensible heat, which is the changing of the temperature, and latent heat, which is the changing of the state of the fluid. And if I add those two things together, that's my total heat. Now, when you look at a product spec catalog for an air conditioning system or a rooftop unit or whatever, you're going to see columns. Is my audio okay? Everybody can hear me? I had a pop-up that said there was an audio problem. Can you guys hear me okay? Someone say yes or no so I can keep going. Yes, okay, good. Then I'm going to ignore that thing that popped up. What the heck does go to meeting know anyway? All right, so when I look at the air conditioning catalog, it'll have columns for total capacity, sensible capacity, and latent capacity. Or some catalogs will give you total and sensible, and they make you do the math to figure out the latent. I don't know why we do that. You can't fit one more column. I don't know, whatever. But you'll get those three different numbers because cooling works the exact same way, right? Just it's a little bit different. So if I took a pressure cooker, and I'm not much of a cook, as you guys know from my pasta example earlier, like here's your spaghetti, kids, let's go. But if I took a pressure cooker, right, I put the lid on, I latch it down, it's a fixed volume. Now I'm going to make you guys flash back here to the old, high school days of PV equals nRT. You can remember that formula, right? P is pressure. V is volume, T is temperature. And for right now, we are going to ignore the N and the R. One of them is to adjust for the type of fluid that I have, right, the specific mass of the fluid. And the other one is to adjust for all these units, so the sloppy mess of units all kind of works out. So essentially what I have is pressure times volume is the linear relationship to the temperature. So in the case of this pressure cooker, I have a fixed volume. The lid's on, it's latched down. I have so many cubic inches or cubic feet of volume. It is what it is. I can't change it without blowing it up, but I don't want to do that, right? So I have a fixed volume. So the volume is fixed. If the volume is fixed and I increase the pressure times volume equates to temperature, the temperature has to go up. If pressure goes up, temperature has to go up, or volume has to go down. But I just told you I can't change the volume on the pressure cooker. So pressure goes up, temperature goes up. And guess what happens if pressure goes down? If pressure goes down, temperature goes down. They have to go up and down together, right? When I look at my refrigeration system, which is going to be my evaporator coil, my condenser coil, and the piping in between them, the volume is also fixed. I don't have any way to make the volume bigger or smaller, right, without blowing up the pipe, which I don't want to do because that's going to be, obviously bad. So it's a fixed volume there. So refrigeration is going to work the same way. When I increase the pressure, temperature is going to increase. All right. So the first thing I need to do is I need to pick a fluid that has a low boiling point. Because if I use my water example at 212 degrees, it's going to be really hard to cool your building with something that's around 212 degrees. It's actually not impossible. You could theoretically use water as a refrigerant. It's just not very feasible. I want something with a low boiling point. That's going to make this work a lot easier. Because otherwise, the air conditioner at your house is going to have to be as big as your house to do it with water. And I'm not going to work with that. So we got to get something with a low boiling point. Historically, what we've used on a lot of systems over the years is Freon R22. And and that has a boiling point of -41. A lot of small systems that we're talking about today, package systems, use R410A. That's a more modern refrigerant, so that has a low boiling point as well. And if you didn't know it, coming down the pipeline here, well, you probably may not even know it, but R22 is actually obsolete. You cannot buy any equipment manufactured with R22 since 2010, and they stopped making replacement refrigerant in 2020. So now you can only get refurbished refrigerant. R410A is on the same chopping block, by the way. And different manufacturers have different solutions they're working on. A lot of them are going to use R54B, but that's a whole nother discussion for a whole nother day because we're still several years away from that discussion, right? But right now, just know that I need to pick things that have low boiling points in order to use them as my fluid. So my evaporator coil, as I told you before, his job is to absorb heat from my indoor air, right? And as he's doing that, it's going to change the state of the fluid coming through. I'm adding heat, which is going to be changing my state, which is a huge energy discussion. Let's look at it all kind of at once, all pieces of the cycle here. So on the refrigeration cycle, I have 4 major components. 2 of them I've already kind of mentioned to you. One is the evaporator coil. That's the indoor piece on a cooling system. His job is to absorb heat from your air. So I send him cold refrigerant, 40-some degree refrigerant. I bring warm air, 75-degree air across him. He absorbs the BTUs from the air, which warms up the refrigerant, and I send it back outside, and it cools down the air. Right? I'm exchanging the heat between the refrigerant and the air. It's a refrigerant to air heat exchanger. The condenser coil is the exact opposite scenario. He's going to have warm refrigerant, and he's trying to reject the heat to the outdoor air. To make this work, I need to have the compressor in there. The compressor has one singular job in life, one job and only one job. And his job, against your beliefs, is not to make things cold. He doesn't do that at all. In fact, he actually makes things hot, which is very counterintuitive. His job in life is to increase the pressure. He needs to go from low pressure to high pressure, low to high. That's his only job in life. Just like if you have an air compressor in your garage for filling up bike tires and basketballs, his job is to take low pressure air from your garage and make it into high pressure air in the tank so it now can be used. That's what he's going to do. Low pressure refrigerant gets converted into high pressure refrigerant. He smashes it down. It's either those reciprocating compressors that we're talking about where it's literally smashing the refrigerant, or it's those scrolls grinding together to smash it, or screws, or some there's all kinds of ways we can do it. But his job is to go from low pressure to high pressure. And if you remember, when I go from low pressure on a fixed volume thing to high pressure, the pressure goes up, the temperature has to go up. That's also counterintuitive. When you're cooling my building, why are you trying to make hotter refrigerant, Ryan? What are you doing? Well, the reason I'm doing that is because I have to respect the heat always goes from hot to cold rule. It was easy over here because I have 75-degree air and a 40-degree coil, so heat goes from hot to cold, no problem, makes sense. But now I want to dump the heat on top on the roof or in the yard of your house or whatever it is. I need hot refrigerant to get the heat to go the other way. So I increase the pressure of the refrigerant, which increases the temperature of the refrigerant. Now in this example, I have 120-degree refrigerant, and it's only 90 degrees outside. So now I can reject heat from the coil to the air outside. And that's why when you put your hand above that fan outside, you feel warm air coming out, right? It's not moving air. It's moving heat from the refrigerant, and the air is only being moved locally outside. It's not taking any air from your house or your building. So the evaporator coil and the condenser coil are kind of yin and yang to each other. One evaporates refrigerant, one condenses refrigerant. The compressor has a yin and yang buddy also. The compressor's job was to increase pressure, and this other device, which there's numerous kinds we can use, just like there's numerous kinds of compressors, but a modern day system is probably going to have a TXV, thermostatic expansion valve. His job in life is to reduce the pressure. He goes from high pressure to low pressure. And once again, this is a fixed volume system, so when the pressure goes down, the temperature will go down. So temperature went down when I rejected some of the heat to the outdoors, right? That got me down into like the 90s for temperature. And then when I go through the TXV, it reduces the temperature again to get me down into the 40s and 50s. So I have cold coil over here. That's my basic refrigeration cycle. And if anybody wants, I have that recorded on YouTube as like, I don't know, a 7 or 10 minute video if you need to explain the refrigeration cycle to someone. So on my heat pump, I got that refrigeration cycle on my AC like normal. When I switch the jobs of the evaporator and condenser, there's a valve in the heat pump. By the way, the only real noticeable difference on a heat pump versus a air conditioner is a reversing valve. Everything else is the same. Still got the same blower, same condenser fan, same indoor coil, same outdoor coil, same kind of piping system. It's all the same stuff. I've just added this reversing system so the jobs of the evaporator and condenser can switch based on the season. That's it. Everything else is the same. So usually the pushback on heat pumps in the north half of the country is that, well, there's a lot of pushback on heat pumps in general, but a lot of them are 1960s, 1970s mentality. If you're from the 1960s and 70s, I apologize to you. But even when I started in the 90s in this industry, and the 90s and 2000s, people were kind of resistant to heat pumps where I live in the Midwest. But now it's more acceptable. One argument was, well, it's just too expensive to install. It's actually not any more expensive than any other system. There's literally nothing else for the installer to do. I take that back. There's one extra thing for the installer to do. The thermostat needs one more wire from the thermostat over to the equipment because I have to tell this valve when to reverse. The thermostat makes that decision. So there's one extra thing to do. You need one extra wire. That's not that expensive to install. Too hard to service. There's literally like one extra component, and maybe you might have a receiver too in there. But you have one extra moving component, and that's the reversing valve. Every other component's identical. So how much harder could it be to service? They're not reliable. I don't know why they wouldn't be reliable. There's literally only one component, and it's not a high failure item. I don't know where that excuse comes from. They're not designed for northern climates. There can be some truth to that, but that doesn't mean we can't use them. It means we can't use them all by their lonesome. If I'm in Atlanta, I could probably do your whole building, your whole house even, right, with just a heat pump. That's probably enough heat. But in a cold climate, maybe I can only get some of the work done with the heat pump, and somebody else, electric heater, gas furnace, or whatever, has to help me out the rest of the year. And I'll explain that. They blow cold air. That was a knock on heat pumps for a long time. As it gets colder outside, there's less heat to grab from the air. There's plenty of heat at 50 degrees, less heat at 30, less heat at 10, hardly anything at negative 10. Right? As it gets colder, there's less heat to grab, which means I can't make your indoor air as warm. So as it got colder outside, people would feel cold blow coming from the register. Now, if you didn't know it, you can heat almost any building in the country. In fact, I would say every commercial building in the country could be heated with 85 degree supply air. It's 85 degree supply air for a long period of time instead of a short period of time of 110, but I could do it, right? But 85 degrees blowing across your 92 degree skin surface feels kind of cool. It's not cool, it just feels cool relative to your body. So people get that cold blow perception. That has been largely solved with heat pumps and specifically with control technology. What we do as the heat pump produces less heat, we sometimes increase the outdoor fan speed to try to grab as many BTUs as possible while decreasing the indoor fan speed in order to increase the temperature. I won't get any more BTUs doing that, but I can increase the temperature. The cold blow problem is largely solved. And then we have the payback scenario. Sometimes there is no payback, and this is a true one. Where I happen to live in Aurora, Illinois, we have really cheap natural gas. Like with all my taxes and fees and everything included, like everything I put in my whole bill and divide it up on my therms, I'm at like 68 cents a therm. And if I look at just like the raw gas, it's like in the 30 cents. It's really hard to pay back a heat pump versus natural gas heating system in that scenario. But in lots of the country, or even where I live, if I just go like 20 minutes further west and people don't have natural gas, because I'm kind of like on the borderline of being in suburbia. If I go a little farther west, people don't have natural gas, they have propane, all of a sudden the math changes. A lot of you guys might have oil in the Northeast. The math definitely changes there, right? So I'm going to show you ways we can get the payback for lots of places. But there's also lots of places we can't do it. We're talking about not being designed for cold climates. These are some of the coldest cities that I've done projects in, and just pulled out some of their weather data just to kind of show you like it can get pretty cold there. And we do heat pumps there. Like we do heat pumps in Minneapolis, Minnesota. Like my company sells them there. We install them there. Well, we don't. The contractor installs them there, right? And in Minneapolis, of the 8,760 hours in the year, 6,500 of them, it's cold. It's below 65 degrees. Sort of depressing. I apologize to you guys in Minneapolis, right? 4,000 of them, it's under 30 degrees, right? 5,000 hours of the year, we're under 20 degrees, and we're still using heat pumps on those 20-degree days in Minneapolis. So if we can do it in Minneapolis, we can do it in other places too, right? I'll skip that one. Look at this one. Here's one for Boston for you guys, showing you that same kind of graph I had before, although this one's a little bit prettier. But now I'm more concerned with the heating side than I was the cooling side earlier, right? But even in Boston, 96% of my year, when I'm in the heating season, it's above 20 degrees. And if you didn't know it, every single heat pump from every single manufacturer that gets AHRI listed, which is all of them, they tested at 47 degrees and 17 degrees outside. They've already tested it at 17 degrees. It can be run at 17 degrees. Anyone who tells you heat pumps have to be turned off at 35 degrees, I don't know where that number comes from. It's a total misconception. It was never true to begin with. Anybody who says that doesn't know what they're talking about. Every single heat pump from every single manufacturer is allowed to be run at 17 degrees or lower. For the company that I work at, the worst one we have can be run at 10 degrees. And we have other ones that we can run down at like negative 20, right? So you can run these things. Now, if I'm in Boston, like a lot of you guys are, literally half of you guys are sitting in Boston right now, or Boston suburbs. If I can get 96% of my heating done at 20 degrees and above, that's a good chunk of the year. All those heating days can be done with a heat pump. Some of these hours can be done with a heat pump too, right? Some of these hours I'm going to need more than the heat pump, and maybe even some of these I might need more than the heat pump, and I'll explain that. But I can definitely use the heat pump. It's not restricted to Florida, right? That cold blow thing, like I mentioned, old school heat pumps had that problem, whereas the temperature coming out of the duct, as it got colder outside, the temperature coming out of the duct would drop and drop and drop. Well, now by playing games with the indoor and outdoor fans, we can keep that temperature consistent coming out of the duct to a point. And at some point, we've gone as far as we can, and the outdoor condenser fan speed is maxed out, and it is what it is. And at some point, the temperature is going to have to drop. But in this example, for this particular project, it was happening at 4 degrees outdoor temperature before I started seeing a noticeable difference in indoor discharge temperature. If I use that same software we've been using all along the past couple days, and I do that exact same weather data, same utility rates, same 10-ton rooftop example, but in this particular case, I am using that same 10-ton gas-fired rooftop that I used before, but now with a 2-speed fan, because I think we all probably agree a 2-speed fan is a pretty no-brainer thing, and an economizer. And I'm comparing that to the same piece of equipment, the same cabinet, if you will, the same cooling system-ish. I say ish because it's a little more efficient on the cooling side. When you get rid of the gas-fired heat exchanger, the cooling system efficiency goes up because I save fan energy, because I don't need as much horsepower to do the static pressure, because I don't have to push air through a heat exchanger. So I got a little bit of fan savings when I did that, and you can see that represented here in the size of the motor that was chosen for the indoor horsepower. But other than that, everything's the same. Same condenser coil, same evaporator coil, slightly smaller motor on the fan, and then no heat, no gas-fired heat exchanger, and I have a heat pump instead. And then I click calculate on my little software tool. And that's going to save me 4%. It's not bad. It's nice. It's not exciting. I'm not going to like start pounding my fist saying we all need to go to a heat pump like to save $85 a year on a 10-ton unit. It's nice, right? But the reason it doesn't save more is because in this particular example of what I chose to do, it's got to run electric heat as well. And running electric heat when it gets really cold, it runs the heat pump and it takes care of me when I'm like, 30, 40, 50 degrees outside. But then when it's like, 10, 20 degrees, I run the heat pump and an electric heater. So yeah, I'm saving some fan energy, right? Yes, I'm saving some gas energy, obviously, but I'm also getting a little bit of a penalty, if you will, on the electric heat portion of it. So in the long scheme of things, I'm going to want to find ways to use less electric heat and more heat pump heat if I can. This particular example is not using gas heat because honestly, gas heat, switching gas heat systems to a heat pump, it's not worth it. It just isn't, unless you have really high gas prices, which you don't, or really low electric prices, which you don't. So with this kind of relationship, it's not really worth doing the heat pump versus gas heat. But what if I'm at a building that doesn't have gas heat, right? They don't have it. It's not even an option, right? It's an all electric building and they're running electric heaters to heat the building. I don't care if it's electric baseboard, electric duct heaters, whatever it is. So the exact same example with the exact same tonnage equipment, et cetera, et cetera, et cetera. In this case, I'm going to go from electric heat to a heat pump. And in this case, now I have a pretty substantial savings, right? because now I'm getting a lot of savings off the heat side, right? And the reason this is going to be the case, so let's say you take a furnace or a boiler, right? A gas-fired thing, a furnace or a boiler or a rooftop unit, right? A gas-fired heating thing. The worst one you could probably buy today would be 80% on a furnace, right? And the best one, the best furnace you could buy would be 98. If you got a boiler, and let's say it's a small boiler for right now, the legal minimum for a boiler as of January for small boilers, 300,000 BTUs and under, is 84%, and the best one I've ever seen is 97, right? If you got a rooftop unit, they're all between 80 and 83%, right? All of these things have something in common. They're all gas-fired. Some of the heat from the combustion process is going to the airstream, and some of the heat is going out the flue with all the bad products of combustion and throwing that outside. Something has to go out the flue at some point in time. Even on a Rockstar furnace, something's going out the flue, 2% of it. Well, when you have electric heat, if you didn't know it, electric heat is 100% efficient. All of the kW that I buy from the power company is getting turned into heat in my building. There's nothing going out of flue at all. It's all going into becoming heat. You could probably argue, well, when I run my electric heater, just like my toaster on my counter, there's a slight orangish color in there, and that's some of the energy being turned into light. So Ryan, you're wrong. It's 99% heat versus 1% light. I'm like, okay, that's fine. That's true. But that light then shines on something in the building and gets converted into heat anyway. So either way, it's heat, right, at some point in time. Now, so you might ask, well, if I have 100% efficient electric heat and all my gas stuff is less than 100, why don't I always just use electric heat? Why do I even use gas at all? Well, because the price of gas is usually, in most parts of the country, less than the price of electricity. So that's why we use a lot of gas-based heating. But if you're in a building that doesn't have a gas, it's not available to you, well, then the math starts changing all of a sudden. Or if gas is expensive, then the math changes. Or if the kind of gas you have is actually propane, and propane is fairly expensive, then the math changes. Or if you don't even have gas, you're stuck with oil, or God forbid, if you still have a coal boiler somewhere, those fuels are relatively expensive compared to gas and electricity. All of a sudden, electricity starts looking good. If I go to a heat pump, though, so heat pump efficiency, at least for like commercial size ones, is rated in COP, coefficient of performance. It's just a ratio of how many units of energy that I purchased relative to how many units of energy I was able to deliver in the form of heat. So those guys typically have COPs that are 2.5, 3, 3.2, something like that. So let's just, for argument's sake, let's say it's between, for an air source heat pump, let's say it's 200 to 350% efficient, which corresponds to 2.0 to 3.5 COP. I don't know why the heat pump guys don't stop using the word COP and start using percent efficiency, because it would make their stuff look so much better, but they don't do it that way. So first argument is, well, how can it be more than 100%? Like, what am I like making power? Like, what the hell's going on here? Well, when you think about the combustion appliances that we talked about before, furnace, boiler, etc., those guys are taking a fuel and converting it into heat somehow, right? The electric heater is taking a fuel, electricity in this case, and converting it into heat. A heat pump does not convert any fuel into heat, not at all. It does not make any heat, zero. All the heat for a heat pump system comes from the outdoor air, or if you happen to have a water source geothermal heat pump, it's coming from, the ground or whatever. But an air source heat pump, all the heat comes from the air. At no point in time does a heat pump ever make any heat. Furnace, boilers, rooftops, electric heaters all make heat. Heat pumps don't make heat. They just move it from outside to inside. They move it. They pump it from outside to inside. So I don't have to pay to make heat. I only have to pay to transport heat. That is why it can be more than 100% efficient. So for every kilowatt hour I buy from the utility company, I'm going to get 2 or 3 kilowatts worth of heat happening in my building. Let's see, a couple questions came up. Okay, he said never mind, do his question, so we'll keep moving on. I'll read it later. I'll give you another example here. This is a residential tool that I use, right? This is a commercial one I've been showing you so far, but I got a residential one. We use a lot of heat pumps on there. And I'm going to show this because it kind of helps me put everything side by side, and I'm kind of lazy. So this case, it was just like a house with a 80,000 BTU system for heating, a 3-ton air conditioner, right, in a Boston area zip code. I used $1 a therm for gas, although I don't know if your gas price has changed since I made this. I use 16 cents for electricity, which is probably pretty close. And then what I did here is the basic system was a simple existing 10-SEER air conditioner that you probably have now with electric heat. And that's how much it was costing somebody to run. It's probably like the worst way you could probably heat your house, but that's what they're doing, right? And I said, okay, what if I take that and I give you like a really good air conditioner? Take that old 10-SEER out and put a 17-SEER in. Great, it saved me $200, which is nice. $200 a year is nice, but in the grand scheme of me spending $8,000, that is not that awesome. What if I say I take it out and I put a heat pump in with a pretty good air conditioner? Now I'm saving $4,400. That is awesome. And now I put a heat pump in with a top-of-the-line cooling system, heating system, however you want to look at it, 17-SEER, high heating HSPF. And now I'm saving $5,400. It's only costing me $3,000 instead of $8,000. So I can start whittling this down pretty quick by making improvements. Going to a more efficient cooling system is nice, but in cold climates, you don't get a lot of cooling hours, so it's not that exciting. The more heating hours you have, the more interesting the heat pump becomes. If you got oil versus a heat pump, this is, once again, it's a residential example, just trying to illustrate it for you. Cooling examples also won't have the same kind of ratio between heating and cooling. They won't have the same kind of ratio because I have more cooling hours and less heating hours in a commercial building than I do a house. But right now I'm not looking at the difference between cooling and heating. I'm looking at the difference between fuels. So if I have oil, here's a story on that. I guess that oil prices, I don't know what you guys are paying for oil these days, but I guess that $2.50 a gallon, my guess is it probably has gone up since I made this chart. Just guessing. But if I look at the same kind of scenarios, if I have an air conditioner with an oil furnace, it's costing me $4,500 in this example to operate that. If I was to give you a better top-of-the-line air conditioner and keep your oil furnace, I could save some decent money on here, right? In this case, the particular heat pump I chose was a dog. It wasn't very good, so it's not much better than going to the high-efficiency air conditioner. But then I picked one that was a really excellent heat pump with a variable speed compressor, and I was able to save even more. It really depends on what you're comparing things to and what your costs of fuel are. We have multiple kinds of heat pumps. I've mentioned thus far air source heat pumps. That means the heat pump is going to use a coil to extract air from the heat from the air outside. I could also have a water source heat pump, which means I'm going to put the coil in water instead of putting it in air. That water could be a lake, it could be a river, it could be a pond, it could be a cooling tower on your roof. It could be city water coming from your faucet, which is horribly wasteful for water, but you could do that. Or it could be a ground source heat pump, in which case I run coils down into the earth, and now I extract heat from the earth. If you think about it, outdoor air in the wintertime, it's anywhere from 0 degrees to 50 degrees. But the ground temperature, once I get below the frost line, the ground temperature is pretty constant. It's going to be in the 50s all the time, right? So all summer long, I could take heat and shove it into the earth and bank it there like a storage buffer, like a battery, a thermal battery. And then in the wintertime, I could take it back out. So these things get more efficient. Air source heat pumps are pretty good. Water source heat pump is a little more efficient because it's easier to transfer heat to water than air. And then a ground source heat pump is even more efficient because I'm banking heat in the earth. The way I can choose to do this heat pump in my building is I can do it with a packaged rooftop like we've been talking about for 2 days. I can do a packaged split system. I could have a dual fuel system where I don't have electric heat as my backup source at all. I have a gas heater in combination with my heat pump. I could do ductless mini splits or variable refrigerant flow, which we'll talk about. And then obviously we have the water source ones. Right? So that refrigeration cycle we talked about before that I showed you on that residential home, I could take that whole split system and shove it all in one box, just like my regular air conditioner. It's literally every single component I would have had in a rooftop anyway, except I got this extra reversing valve in there. Other than that, it's the same deal. Right? One extra thing, reversing valve. I could do it as a split system. It's the same stuff I'd have on a cooling split system, right? I'm still going to have a condenser coil, still going to have a compressor, still going to have an evaporator, still going to have a blower, still going to have a condenser fan. I just added that reversing valve. One extra component, nothing different there. I can have a dual fuel system. This is not super common commercially. It's more residential, although light commercial buildings tend to have residential equipment in them, quite honestly. Little storefronts where you got a shop in the back and you got like 5 offices in front. They tend to put a residential system in a lot of those buildings, right? But if you do that, You could do it with a dual fuel system where you can combine your gas furnace with a heat pump. Only one component different than if you had a gas furnace with an air conditioner. That's a reversing valve. You can have ductless mini splits. I'm sure you've seen those numerous times. And nowadays we also have ductless mini splits that could have multiple indoor heads, multiple types and multiple. So historically it was you had this one indoor unit and you had your outdoor unit. Now I can have this outdoor unit piped to 4 different indoor units. It can be 4 of these high walls. It can be 2 high walls and 2 of these cassettes that go up in the ceiling grid, right? And I can have those be in different offices of the building. And that's a great way to take care of a small office building. Everybody gets their own thermostat, but I still only had to buy 1 outdoor unit. Now I did have to buy 4 indoor units, so there's some cost there, but at least I only had to buy 1 outdoor unit. If I do the water source stuff, I got multiple options there as well. This is going to typically be for larger buildings. You're not going to have typically 1 water source heat pump at, like, say, your house. You could, but it's not super effective. What I want to do is, so my refrigerant system, when it sends the hot gas from the compressor out to the condenser coil is not a coil sitting outside with air blowing across it. It's a water loop. The refrigerant goes and floods this tub, if you will, and then I run water through it. And the water picks up the heat. I have 85-degree water coming in this example. It picks up all the heat from my refrigerant system, and now it has 95-degree water that sends out to the cooling tower to reject the heat outdoors. And on my refrigerant side, I have the BTUs coming in and out. Water source heat pumps can be fairly effective, on bigger buildings, because what I can do is I can have some zones that want cooling, and they're running their compressor in the cooling mode. Other zones may want heating, and they're running in the heating mode by reversing that valve. And the ones that want heating are taking heat off of the water loop in the building. And the ones that want cooling are putting heat onto the water loop in the building. If I have some people using heat and some people taking the heat, guess what I don't have to do? I don't have to send very much heat outside to be rejected by the cooling tower. Or in the winter, my cooling tower shuts off, I run my boiler to heat that loop. I don't have to run my boiler as much, because half the zones that want heat are getting it from the ones that don't. So zones in the middle of the building don't have any real heating load. Think about it. If you're the center of the building, not by the windows, you're the center of the building, and you're on a middle floor, the people on the left of you, right of you, front, back, up, and down, it's always 72 degrees for those people. It's San Diego. You're not even outside. You don't even know you're in Boston on a 9-degree day, because everybody on all 6 sides of you is 72 degrees. So you don't need any heat. So the interior of the building can send its BTUs of heat to the perimeter of the building that does have glass windows and does need heat. And I don't have to run anything else to do that. So it can be really efficient on a large building to do these water source loops. You could do water source geothermal loops, which I had mentioned, right? So that's where I'm taking, it's the same stuff on the inside. All these kind of same heat pumps in here, right? Rejecting their heat to a water loop. But instead of having the water loop connected to a boiler to supplement the heat, or a cooling tower to supplement the cooling, instead of doing that, I don't buy the cooling tower or the boiler, and now I send the heat in the summertime down into the earth. I dump it into the earth. So my ground temperature below the frost line, instead of being 60 degrees, becomes 62, 65, 68 degrees as I'm banking heat down there all summer long, which is cooling off my water to bring it back to my building to absorb more heat. And then in the wintertime, I have all this warm ground. I have 70-degree warm ground. I start extracting that heat back out and sending it into the building. So the ground temperature is going down all winter long, 70, 68, 65, 63, 62, 59, etc., as I'm taking the heat back out. It's like a nice buffer in capacity. It's extremely efficient. It's more efficient than the water source job by itself. The water source is more efficient than air source, and then the geothermal is more efficient than traditional water source. Now, if I have a large disparity between my heating and cooling needs on an annual basis, like if you're in Atlanta, it just works, right? Oh, I have as much heating that I need, as much cooling I need, so I throw all the heat in the ground all summer, and I take it all out all winter. Sounds great. Well, if I'm in the north half of the country, I have more annual BTUs of heating than I need of cooling. So in those cases, what I'll do is I'll put a small boiler in to supplement the loop. So I'm getting all the heat out of the earth. Everything's great. I'm barely ever having to run the boiler. And then maybe by the time I get to March, I got to run the boiler a little bit more, right? So I'm going to size this for like the smaller of the two needs, heating or cooling, which means that I am going to have a boiler supplemented. Now, if I'm in Miami, it's the opposite thing. I'm going to size it for the smaller of the two needs, which is heating. I don't need that much heating. And then my supplemental device is a cooling tower. So I'll combine cooling tower with geothermal in the south. I will combine boiler with geothermal in the upper north, right? And in the middle, probably don't need either one, right? Every job's different, but conceptually, that's what I'm telling you. Now, the other thing I didn't mention, and I should have mentioned, when I have these systems, right? Let's say it's this one here, the split system, right? It's all the same as a regular cooling system, right? And I'm sizing this for either cooling or heating. It's probably not likely I can size it for both. Once again, if I'm in Georgia, maybe it's equal. Maybe I need 10 tons of cooling, 10 tons of heating. Everything's perfect, right? Well, here maybe I need 10 tons of cooling, right? But maybe I need 15 tons of heating. And if you didn't know, and you're not used to hearing heating referred to in tonnage, it's 12,000 BTUs for every ton. So if I need 15 tons of heat and 10 tons of cooling, I have two choices. I can either size this whole system for 15 tons of capacity, which means my cooling system is oversized, which means I'm going to have problems dehumidifying. And I don't really want to do that. So that's not really a good idea in most cases. Sorry about that. I'm losing my voice. I'm going a little Peter Brady over here. If you don't know who Peter Brady is, Google it, folks. You're going to love it. Excellent show. In any case, I'm going to have to size it for the cooling need in order to make sure I get my dehumidification and staging control right, which means I'm going to be short-handed on the heating side. So when it gets really cold outside, I'm going to have this electric heater on here turn on to supplement the heater. I do not turn the heat pump off. I continue running the heat pump. Even when it's 0 degrees outside, I'm still getting some BTUs out of it. I use the electric heater to supplement the heat pump. Now, if you want to, you could buy no electric heater and you can go 100% heat pump and have nothing else. And you can get a heat pump that'll do all the work for you on a negative 20-degree day if you want. But it's going to be a really big unit and oversized for cooling. So you better have a lot of turn down capacity. It better be variable speed compression, and it better have excellent turn down capacity, or you're going to get screwed on the cooling side. All right. Let's get it back over to where we were. All right. If there's no other heat pump questions, what do we got? It's 10:38, so we still got like an hour. We're doing good. All right, let's go into variable refrigerant flow systems. All right, variable refrigerant flow systems are heat pump systems. You could get a cooling only one. That's a thing. It's available in the world. It's just not available in the United States. So as far as we're concerned here, all VRF systems are in fact also heat pump systems. Now, I'm going to use variable refrigerant flow, which is the generic term. There's also what's called variable refrigerant volume, VRV. That is one specific manufacturer's version of VRF. It's just like a trademark name. It's like a Kleenex type name, right? Versus tissue. So I'm just going to use the generic one, VRF, right? So every VRF is a heat pump, right? So everything that we talked about works exactly the same way. What is going to be different is that I'm going to have the refrigerant varying, and I'm going to have lots of zones. So in this example that I'm showing you here, the first thing you notice is I have 2 outdoor units. That's not always the case. You may have 1, you may have 2, you may have 3. In this case, I have 2 of them, and they're manifolded together to operate like 1. Now, there's a couple reasons to do that. One, if the manufacturer designs their system that way, and let's say that every module they make is, 6 tons. Well, I can have 6 tons, I could have 12 tons, I could have 18 tons by putting 3 of them together, right? It's easy. It's less things for them to manufacture. Instead of them manufacturing a 6-ton model and then also manufacturing a 12-ton model, right? They can just make a 6-ton and say, well, just connect the 2 together, right? So that is one reason why you might see multiples on there. And all the other thing is it helps out with staging. If each one of these units has 2 compressors and I manifold 2 together, now I have 4, right? And I'm going to do it with variable speed compressors. So I have a lot of ability to modulate down by having lots of compressors, each of them modulating. The other thing you'll notice is I have multiple indoor units on here. This is showing 5. I could have 10. I could have 30, right? I could have all kinds of quantities of indoor units on here. The limitation is going to depend on the limitations that each manufacturer gives you. But as a general thought process, you should be thinking 25, 30, 35, 40 zones maximum. Most jobs are probably going to have 6, 8, 10 zones, but you could do more. And most manufacturers, actually now all manufacturers, will allow you to use different types of indoor units. We got that traditional high wall ductless unit that a lot of you can visualize in your head. We have these cassette style units that insert up into a 2x2 drop ceiling grid. Actually, they're a little bigger than that, but insert up into a grid like that. And I could also have ducted units. I could have ductless systems, which it bothers me. Every time I say it, I'm bothered by it. But as a general grouping, these are always kind of thought of as to be ductless systems because usually they're using this kind of thing. But you could put ducted ones on there, right? And then I can have ductwork go into 2 or 3 small rooms. These guys are all going to have a communication card built into them, as are the outdoor units. They all come with DDC control standard. You can't get them with basic controls. It's always communicating DDC controls, and it has to be the controls from the manufacturer of the equipment. You cannot say take a Johnson Medisys system and put it on, say, a Toshiba VRF system. That's not an option. You got to use Toshiba controls on Toshiba, right? Everybody's system comes with the controls included, standard, free, however you want to work it. And you cannot use someone else's controls. Now, the building could use someone else's controls. I could have a Johnson Medisys building automation system that's controlling, like, I don't know, my boiler plant and my lights or something like that. And then I could have this Toshiba VRF system, and I can make the Toshiba system talk to the Johnson system. But the individual cards and widgets in these devices have to be these Toshiba ones. Or Daikin, or whatever brand, Mitsubishi, whatever brand you're thinking of in your head, it's all specific to them. So I can't take a Toshiba system and remove this unit and drop in a Mitsubishi unit on this one indoor unit. Can't do it. It's got to be all part of the same family. The reason being is I have variable speed compressors. I have lots of compressors. They're variable speed. I have multiple condenser fans. They're variable speed. I have modulating, communicating EXV controls instead of standard TXVs. I have multiple speed motors in here. All of those things have to be coordinated together. So they have to all be in the same control system in order to do that. Oh, geez. Thank you, Lori. Lori just gave me a reality check. I'm thinking I have like an hour and 20 minutes left. I have 20 minutes left. Sorry. The fact that this is, that most people on here are in Eastern time and I live in Central time and I'm trying to do the adjustment in my brain. Yeah, you are correct. We have 17 more minutes together. All right, sorry about that. I was thinking like, dang, I got to fill like a bunch of extra slides. The good news is I still have 200 more slides after this because I was prepared to go down the rabbit hole of other topics that we didn't advertise in case I needed to. I don't have to do that now, obviously. We'll just wrap up with VRF like we had planned. Okay, thank you, Lori. That helps out a lot. Greg actually asked a good question. Is oversizing still a problem with VRF? Yes, oversizing is always a problem for all systems. So the heat pump I showed you before, the inverter-driven compressor on the rooftop we talked about, those things help, but it's still a problem. So if I only have 1 or 2 stage equipment, oversizing can be very problematic. If I have variable capacity equipment, oversizing is still an issue. It's just not as bad. The reason it's still an issue is I lose turn down ability. So I'm going to make a simple graph to kind of illustrate that. All right. So right here I have a unit, right? And over here I have another unit I could choose. Let's just for argument's sake say I have a 10-ton unit or I have an 8-ton model I can pick. Right? If I have the 8-ton model, and let's say both of them for argument's sake, and just to make my math easy, let's say they have the ability to modulate down to 10% capacity. They can modulate from 10 to 100. There is no compressor or fan or pump or gas valve or anything that can modulate down to 1%. They all have some limit on them, right? For gas valves, it's typically 40% is the minimum. For pumps, it's typically 20%. Fans are often 30%. Those are just kind of check figures, right? But let's just say this compressor can go down to 10%, which is really good, right? So if I put the 8-ton unit in, he can go down to 0.8%. If I put the 10-ton unit in, or 0.8 tons, he can go down to 1 ton, right? And let's say I had another choice. Let's say it was a 5-ton, and that's what I really need is 5 tons, right? So he can go down to 0.5 tons on his modulation. And this is assuming I could find one that go down to 10%. That's pretty rare. The more oversizing I do, if I wanted to put a 5-ton in for cooling, but I said, well, let's put an 8-ton in so I can get more heat out of this thing. Well, now I can't go all the way down to 5-ton, half a ton when I need to. I can only go down to 0.8 of a ton. And if I say let's double it to get all the heating done with the heat pump, now I can only go down to 1 ton instead of a half a ton. So where this becomes a problem is on jobs that have lots of zones. If I only got 5 zones, this oversizing thing is probably fine. But if I got 40 zones, and some of these zones are like, 5,000 BTUs, 9,000 BTUs, little tiny things, and I can't get down to their capacity needs, then it starts becoming an issue. So, and this is true for boilers and chillers and stuff like that too. The more oversized you are, the less turn down you have, which means it's harder to take care of little zones. They got to wait for a big zone to call, if you will. Hopefully that relates to it. Robert is asking about VRFs and possibly downsized leaks. Yeah, let me talk about that separately, though. That's coming up. So let me get through some of this here. All right. So VRF's been around a long time. I won't go through the whole timeline with you. Just know that this is, in fact, a 40-year-old technology in other parts of the world. In the United States, it's probably like a 15-year-old technology, right? So it's pretty established in the United States, but it's really established worldwide. Oh, why did I have that in here? Dude, don't care about. Okay, hang on. Discard. Need to go to Boston. Why do I have the non-Boston slides on here? There's Boston. That was weird. All right. As you can see, I've done this in other towns too, right? So in Boston, you've seen this chart 15 times from me already. I'm designing for this day, a 4-degree day in Boston or whatever, and a 91-degree day in Boston or whatever it is. I'm designing for those days, but very little time is it actually operate there. Part load is where it's at. Middle operation is the interesting thing for both cooling and for heating. If I could be more efficient there, that's awesome. And VRF is one way to do that. All right, the reason why VRF is becoming popular compared to other systems is I can move a lot of BTUs through refrigerant, and I cannot move as much through water, and I definitely cannot move as much through air. Air is by far the least efficient mechanism I have for transferring energy around a building. But we have a lot of systems in the United States that are air-based. In fact, we're the only ones that do that. Pretty much air-based systems, that's like a United States and Canada type thing, right? It's a North American thing. When you go to Europe or you go to Asia, they're not having these large, giant commercial air handlers, VAV systems, things like that. They don't do that. They do a lot of water systems in Europe and a lot of refrigerant systems in Asia, where they don't have any ducting or very minimal ducting just to take care of ventilation. Another way to look at this is, instead of looking at how many BTUs I can hold, is to look at how big does my system need to be, physically how big does it need to be in order to move that energy. So what I can move with a small refrigerant line set, I can move with a slightly bigger water piping system. But if I want to do it with duct work, I need a 16 by 48 inch duct to move that much energy. So 2 little tiny pipes or a big 4-foot wide duct can move the same amount of energy. One more way to look at it, these pipes right here are doing 40 tons of cooling. This ductwork is doing 12 tons of cooling, and it takes up more space. So for buildings that are space constrained, it becomes really interesting to start looking at not using duct systems. And for a lot of older buildings, right, you got buildings that are built prior to the 1960s, they probably don't have very much in terms of ductwork going on. So if I want to start retrofitting cooling onto some of those heating-only buildings, VRF is a really good way to look at, start doing that. If I do a 2-pipe VRF, that means I have 2 pipes going around the building from the outdoor unit to all the indoor units, and it can either be in the cooling mode or in the heating mode. Everybody gets cooling or everybody gets heating. Nobody can mix and match in that particular scenario. Now, they could choose to have nothing. They could shut their valve and take no heat. But this guy right here can't ask for cooling. Well, he can ask for it, but he won't get cooling when everybody else is asking for heat. They basically just take a vote, majority rules. Hey, most of us want heat. We're going to do that. You're going to have to just like shut down and do nothing for a while. Sorry, bud. Right? That's what a 2-pipe system is. And you can do that, and it's okay for small systems, right? So you got 1 outdoor unit, 2 pipes running around going to all your indoor units. You're also going to have thermostat wire going down the wall to some kind of sensor on the wall. And then all these things are communicating. So you're going to have a communication cable going from one unit to the next, to the next, to the next, to the next, to the outdoor unit. So they can all share data. The way that sequence of operation is going to work is that zones have certain capacity needs. In this case, you're looking at here, I got 3 tons, 3 tons, 2 tons, 2 tons. So I have a 10-ton worth of installed capacity on the indoor units, but I only put a 3-ton outdoor unit in. I'm going to take a diversity credit, just like we do on VAV. I'm going to bank on the fact that not everybody wants maximum cooling or maximum heating at the exact same time, and I'm going to downsize my outdoor unit. I'm not going to do it randomly. I can look at the loads for each of these guys and look at the time of day they're going to peak and decide when I can do it and how much. But as a general thought in your head, most systems that have decent quantity of zones can have a 20% reduction in the sizing of the cooling plant. This is true for VAV, VRF, water source heat pumps, etc. The other thing I could do is typically referred to as a 3-pipe system. That guy has, as you would imagine, 3 pipes running around the building instead of 2. So I'm installing 1 extra pipe. And that pipe goes, in this example, is going down this middle hallway. And then I got these little yellow boxes. 3 pipes go into the box, 2 pipes go out. It's like Mad Max, right? Beyond Thunderdome. 2 men go in, 1 man comes out. In other case, 3 go in, 2 come out. So it's not exactly the same, I guess. My 1980s references aren't helping me here. But 3 pipes go in, 2 come out. This unit outside is sending both, let's just think of it this way. He's sending both cold refrigerant and hot refrigerant to the building. And then each zone is picking whether he wants the cold pipe or the hot pipe. So these guys over here are all asking for cooling because maybe the sun's shining on their side. And these guys over here are asking for heating. Right? He can do simultaneous heating and cooling for the building, whereas the 2-pipe could not do that. So 3 pipes running around the building instead of 2. So that's 1 extra thing to install. And then I also have this converter box to install that has 3 pipes going in and 2 going out. But then this stuff, this is the same indoor unit I just showed you, same thermostat, same communication cable, right? Just 1 extra pipe, extra box, and a slightly different control sequence in this outdoor unit. I'm mentioning 2-pipe versus 3-pipe. There are other ways to do it depending on the manufacturer of your choosing. This middle example is that 3-pipe way to do it. What you could also do is have everything be 2-pipe, but have it all home run back to a box. So these little boxes that we're switching between 3 and 2 pipes, I could essentially grab them all together and put them in 1 large box and do it that way. The advantage there is I only have to run 2 pipes out to each individual zone. Right? So you might want to do it that way. Depends on how your building is laid out. These pipes now become fairly long, and there's a lot of them. So if my building is laid out this long, skinny building, this pipe drawing on the left would have a lot of piping compared to the middle drawing. But the drawing on the left would have less piping connections. So less places to have a field air there. But I have to buy more pipe. Versus if my building was more squarish, right, then maybe it becomes more equal. There's also a third scenario, which is kind of a hybrid of those two. So in this case, everybody didn't get their own little converter box to go from 3 to 2 pipes. I've grouped them. So these 4 guys on the right have 1 converter box, and 3 pipes come in and 2 pipes go out. But that means all 4 of these guys have to choose heating or cooling as a group. So this group can choose something different than the bottom group, but internal to the group, they can't get something different. All right, let's look how this works. So this example here, I know it's pretty busy, but over here in the red dotted line is my outdoor unit. In this example, it's an 8-ton VRF outdoor unit, and I have 5 zones inside over here, and I have a 2-ton, a 2-ton, a 1-ton, a 1-ton, a 2-ton. So I have 10 tons connected to an 8-ton unit, once again taking a diversity credit. If all of those guys are in the cooling mode, maxed out, they all want max cooling, okay, fine. I turn on both of my compressors. In this case, I have an AC and a DC compressor. So the DC compressor is variable speed, the AC is on-off. But in this case, I ramp the DC up and I turn the AC on. Everybody's full capacity inside, full capacity on the compressors. I open up all the valves and I use the full condenser capacity. It's basically like one giant air conditioner at this point. If everybody wants maximum heating, exact same thing happens. All the indoor units open up all their valves. Compressors ramp up fully. The outdoor condenser coils open up their valves. The only difference is I got that reversing valve happening, so evaporators and condensers change jobs. But other than that, it's like a giant, huge heating system, a heat pump system. And neither one of those are interesting things. Where it becomes interesting is if somebody wants heat and somebody wants cooling. Now, you can't do this on all VRF systems. Only ones that have that, that third pipe, that simultaneous heating cooling system. Some of them call it simultaneous heating cooling. Some of them call it heat recovery. Some of them call it heat reclaim. They have different names for it. Different manufacturers do. In this case, I have 2 zones that are happy. They don't want any heating and cooling. They're good. Great. One zone that wants 1 ton of heating, 12,000 BTUs, and then 2 zones that each want 2 tons of cooling. So I need 2 tons of cooling and 1 ton heat. Historically, I would have ran air conditioning for 2 tons and then ran my electric heat or my boiler or whatever for this 12,000 BTUs, right? I'm not going to do that in this case. In this case, I got these 5 tons of total need. I'm going to turn one of these compressors on, ramp it up to get me 4 tons of capacity to do 5 tons of work over here. And then the outdoor coil, I'm going to shut one of them off in this case and open the other one up for 3 tons of condenser coil surface area. So I'm going to run these 2 tons of cooling, and I'm going to use that, or 4 tons of cooling. I'm going to use that compressor to move the 4 tons of refrigerant, and I'm going to have them reject 3 tons of their heat outside, but then reject the 4th ton into that zone. So this guy is a condenser coil. This guy is a condenser coil. These 2 are evaporator coils. I always have to have as equal amount of evaporator coil as condenser coil. I have 4 tons of evaporation. I have 4 tons of condensing. I am good. It's just that instead of that 4th ton of condensing outside, I cut that coil out, I picked them up, and I walked them over to zone number 3, and I stuck them over there. So he's getting his 1 ton of heat from his neighbors. So I'm getting 5 tons of heating and cooling for the compressor KW of 4 tons and the heat rejection price of 3 tons. If it's the opposite, I have more heating than cooling. So in this case, I have 2, 2, 1, 1. I have 6 tons of heating, 2 tons of cooling needed. So now I turned on the AC compressor for his 4 tons. I ramped up the DC compressor for 2 tons to get a total of 6 tons. I have 6 tons of heat working with my 6 tons of compressor. So I have 6 tons of condenser surface area. I have 4 tons of evaporator outside, 2 tons inside. So I'm getting 8 tons of heating and cooling capacity for the compressor horsepower of 6 tons for the heat rejection price of 4 tons. And then if anybody asks what happens if it's exactly the same, I have 4 tons of cooling, 4 tons of heating, exactly the same. Then the coils outside completely shut off and the condenser fan shuts off, and I don't reject any heat outside or take any heat from outside, and I use my compressor as a circulating pump between my zones. So I'm getting 8 tons of heating and cooling capacity for the compressor, 4 ton power, and 0 going out with my heat rejection price, no condenser fan power. Lots of building types have been doing this. There's all kinds of various applications. In the interest of time, I'm going to skip some of these examples. These are just buildings that I'm familiar with personally, but I'm going to skip those in the interest of time. Just know at this point, these are all buildings that are literally like, 45 minutes from my house or less. And this list is from 10 years ago. So the list is so much larger now. There's a lot of buildings doing this. If I want to figure out how much the VRF is going to cost, I got lots of factors to take into consideration. Energy cost is a big portion of that. Labor cost might be a big deal. Now, if I don't have a duct system, I have a heating only building, and I want to add cooling, a VRF system becomes very attractive because I don't have to pay for any duct work. But if I already have a ductwork system that I own and it's in the building, well, now the labor cost to do VRF starts getting unattractive because now I got to pipe a bunch of stuff versus just swap out my ducted equipment. So there's that trade-off there. I got to factor in the building automation control because some systems need me to add building automation. VRF already has building automation built in. So when I compare one to the other, I got to make sure I have everything included. Don't just say, well, the rooftop VAV costs less, but you didn't account for the cost of the control system. Put all the stuff in there for the one system and put all the costs in for the other system, then compare them. And then sometimes there's other advantages for space constrained places where I don't have anywhere to put the ductwork. I can't physically fit it in the duct chase, in the pipe chase. Piping is smaller, so it might fit. So if I look at a VAV rooftop, which is a common system, right? I got this rooftop similar to what we were talking before, but it was bigger. And I got all these VAV boxes, 30 of them out there. I want 30 zones of control. So I got to compare those things. Add up my VAV boxes, add up my rooftops, add up my indoor VRF, add up my outdoor VRF, add my controls to the VAV, because that's a third-party thing. VRF, it comes with it. VAV, you got to get a third party to do it. Add all those things together and compare them. But in most cases, the VAV rooftop unit is probably going to be less expensive than VRF. Not always, but usually. Unless I have a space where I can't fit ductwork, all of a sudden VRF starts winning. If I look at a more complicated VAV system, same VAV boxes, but now I have an air handler and a water-cooled chiller and a cooling tower and a boiler plant, and then the controls for all that, and now I compare it to VRF. A lot of times the VRF can win that battle from a first cost standpoint. So there might be some opportunities there. The bigger the building gets, the less the cost per zone gets up here. So yeah, if I got like a university campus, this starts becoming pretty exciting, or a hospital or whatever. But if I got a smaller building, then this becomes more interesting to me as a general rule. From an energy standpoint, unfortunately, all the kinds of systems we've discussed today, you cannot easily compare one to the other. You can compare one rooftop to another rooftop, one heat pump to another heat pump, one VRF to another VRF. But if you want to compare a VRF to a chiller, or a VRF to a rooftop, or a gas rooftop to a heat pump, now it becomes complicated because they don't have the same kind of rating system. Each type of system has its own rating system with its own test, and there is no conversion formulas between those types of things. So on the cooling side, when I have small systems, they get rated residentially with SEER, like we talked about last week. The big systems get EER, full load efficiency, and IER, part load efficiency, and there is no formula whatsoever to convert SEER to IER because they are separate tests operated at different temperatures at different cycling rates. So there's no comparison formula between the two. And I got chillers. They have their own EER and IER, and a chiller IER is not the same as a DX IER. It's a different test also. Plus, on a chiller, we don't include any fan or pump energy. The pump energy to get the water to the air handler, the fan energy to get the BTUs from the air handler to the space. Those don't get counted in there. Well, on a split system, we don't have pump energy, and the fan energy is counted in there. So you can't look at a chiller efficiency and compare it to a rooftop efficiency and say, well, this one's more efficient. You can't, because you got to add everything in, and you don't have everything totaled up yet. Heating is similar. We've already mentioned those different ways we do heating efficiency, so I'll skip that in the interest of time. But once again, it's very hard to compare directly. I can do it at the full load stuff by converting COP to a percent or converting percent to a COP, but it gets hard to do it at the part load thing. So then I need to do some kind of software to do that, right? And I haven't even mentioned VRF yet. So VRF efficiency ratings are more complex than all of those because they do heating and they do cooling, and it's a newer technology. So when AHRI had developed that rating system, they developed it to take into account some of this part load stuff a little bit better. So for every VRF system, there's different kinds in the directory. You can pick air to air, water to air, right? Heat recovery, no heat recovery. But for all of those, I'm going to have multiple things to look at. First off, they're going to give me an EER for full load at 95-degree outdoor temperature. That is fairly worthless because, once again, we hardly ever operate at full load, so who cares how efficient I am there? They'll give me a part load. That is useful to me. I have an IER for that, and it's kind of like the rooftops where we heavily weighted the middle capacities, which makes sense, like we talked about last week. I'm going to have a heating COP. In fact, I'm going to have two of them, one at 47 degrees outdoor temp, one at 17, just like we had for those other types of heat pumps. And if they have water source, there's ratings for that. Always keep in mind, for the COP of a heat pump, any kind of heat pump, including VRF, it in no way takes into account any supplemental heat you need. So if you size it for cooling, meaning you don't have enough heat, you have to somehow later in your calculations account for the fact that you got to run an electric heater somewhere. And then, not only do you get the heating and cooling ones, but for VRF, if you're doing heat reclaim, heat recovery type VRF, you also get SCHE, because we were short on acronyms in our industry. So simultaneous heating and cooling efficiency. You get one more rating on there. Now, this is kind of a moment in time. For this rating, it is assuming 50% of the zones in the test are in heating mode and 50% are in cooling. That's not going to be the case very often. You might have 20% in heating and 42% in cooling, and other ones need nothing. But in order to get a rating, they pick something and say, hey, let's just pretend it's a half cooling, half heating. Let's just see how good you can do. So you have that rating on there as well. All right, so for any heat pump, you can pull up the rating on the AHRI directory, just like you could for rooftops and boilers and heat pumps and everything else. You could do it for VRF and pull up these ratings and see the kinds of efficiencies that you're going to be getting on here. Right, so you're going to be getting pretty high IERs, way better than the rooftops we talked about. Right, pretty good COPs on the heating side. Right. And then I'm going to have these combined efficiencies. So I have, like, for example, on this first one, I have 16 part load efficiency for cooling. I have a COP of 3.2 on a 47-degree day, 2.2 on a 17-degree day. Those are all really good. And I have a combined efficiency, so a combined IEER of 24.78, like way better than I have on cooling only, because I'm basically giving somebody free heat. All right. Water source heat pumps, for VRF get the same kind of thing, just a little bit different, obviously. You can print a certificate for any one of those. There are code required minimums. They haven't really changed since the ASHRAE 90.1 2013. They're basically the same as we have now. And now we have them in the IECC 2018 as well. They used to only be in ASHRAE, not in the energy code. Now they're in the energy code. It doesn't take a lot of thought on these because it's really hard to find VRF that's not code compliant. It's also efficient. It pretty much all hits the code minimum. But you got to double check to be sure, but it pretty much all makes it from every model. All right, I'm going to skip all those tables because that's kind of boring. If I want to compare this to other systems, in this particular example, we have VRF in red, and then we have code minimum compliant air-cooled chillers in green and code minimum compliant water-cooled chillers in blue. And VRF is more efficient than pretty much all of them. Now, could I get a non-code compliant chiller, or a code compliant chiller that's better than code, one that's a stud chiller? Absolutely. Can I get a chiller that'll beat VRF? Absolutely. But if I just look at the minimum code ones versus the minimum code VRF, VRF pretty much always wins. When you compare VRF to chilled water plants, which is a very common comparison, like I mentioned before, it doesn't take into account everything. VRF has everything built into the efficiency number. All the energy required to make the cooling, all the energy required to distribute the cooling. Chillers don't work that way. They just have the energy to make the cooling. And then after that, so in green is my chiller efficiency at various load points. After I count the chiller, then I got to add the energy of the cooling tower. Then I got to add the chilled water pumps. Then I got to add the condenser water pumps. Then I have to add the air handler fan energy. And once you add all those things in, the chiller doesn't always beat VRF. Could I get a better chiller? Yeah. Could I get a better pump? Yeah. Could I get a more efficient cooling tower? Yeah. Could I get a more efficient air handler? Yeah. My point on this, though, is you just have to add all those things together before you compare them to VRF. And then you get a more fair comparison. Because VRF is an all-in deal. It's all in on price, meaning you get all the controls with it, whereas traditional systems don't have controls with them. It's all in on energy, meaning everything's built into the efficiency numbers, whereas traditional systems, each widget, chiller, cooling tower, pump, fan, has its own efficiency rating. The best way to do this is with energy modeling software. There's not any easy way to do it. Lots of software tools already have VRF model numbers built into them, which makes things easier. If you want to make your own tool, that's fine. The problem you're going to have there is you're going to struggle to get data from the VRF manufacturers, at least detailed load data. You're going to struggle to get it. They're probably not going to want to give it to you because they're nervous that you're going to share it with their competitors. Whereas these folks that make the software tools, they have the data because either they are already the manufacturer or because they're pretty well-known software companies and they set up deals with the manufacturers. Some tips if you're using cold weather applications. Oh, geez, I'm already 8 minutes over. All right. Okay. If you have to leave us, I totally understand. No offense. If you can stay, I'm going to keep talking for like 7 more minutes because that's what I do. But if you got to leave, I get it. It's been nice talking with you guys. Send me emails if you want any follow-up stuff. If you can hang out for a few minutes, cool. I'm going to keep explaining stuff. Sorry, Alberto. I've never once been on time, so why make it be this time? Some tips on cold weather applications. One thing we've done on various applications is we've actually put the outdoor unit indoors. And that sounds kind of hokey, like what the hell are you doing putting it indoors? We put it indoors, and we have louvers in the wall to suck air in, and the condenser fan on top, we duct it to outside. So it's basically outdoors. Like, well, why the hell are you doing that then? Why don't you just actually put it outdoors? Well, you can. When I put it indoors, what I can do in that case, when it's so cold outside that the heat pump can't do all the work on its own, instead of having an electric heater at every single zone to turn on, what I can do is turn on a heater in this room, which warms up this air that's getting sucked in and makes it not be 0 degree air, and all of a sudden it's 28 degree air or whatever. So now the condensing unit, the outdoor unit, thinks it's a warmer day outside and it can make more heat for me. But I can do it with one heater in the corner, or 2 or 3 heaters in the corners, as opposed to a heater in every single zone. It's just an easier, less expensive way for me to get electric supplemental heat to the system without having to run extra wires all over the place for individual heaters. So I could do that if I want to. It's a unique little trick that some buildings have taken advantage of. Someone asked about refrigerant leaks. All right, and if you're going to have a lot of refrigerant pipe running around the building, obviously refrigerant leaks is something you should pay attention to. We have a standard for that, not just for VRF, but for all systems. It's ASHRAE Standard 15 for refrigerant safety. So it applies to all systems, including VRF. the things you have to think about are, how big is my smallest zone? How many pounds of refrigerant do I have? What's the limit for my space? There's defined maximum refrigerant limits for each kind of space. And some spaces have higher limits because those spaces are ones where people can't help themselves, if you will, right? If I'm in an office building and something's not right, I could leave. I could walk out the front door and save my life, right? But if I'm a kindergartner or I'm in a nursing home, right, I can't get myself out of the building properly, then I have lower limits for those places, because those places are institutional occupancies where they need assistance to exit the building if something really, really bad ever did in fact happen. Really small systems don't have any concern, like there's so little refrigerant relative to the space, you don't have to worry about it. If you're doing a lab building, not part of this discussion. We're talking about offices and retail and schools and nursing homes and those kind of things. There are some articles to help you out on how to properly apply these safety standards specifically to VRF. I'm going to give you the cliff notes of those things. First off, if you're having trouble meeting the limits, right, because the limit is 25 pounds of refrigerant maximum on my circuit into my smallest zone. Per 1,000 square feet, but I'm looking at it from my smallest zone's perspective. If I have one little tiny zone on my VRF, some little dude's private 8x8 office, and that's causing me to hit this limit, take that guy's zone off of the system. Don't put him on the VRF. Give him his own little mini split or something like that. And then it only has like 1 pound of refrigerant and he's fine, he's on his own. So if you take the smallest zones off of the VRF, if you're having this problem, take the smallest zones off the VRF and give them their own equipment. Now my smallest zone that I have to think about is a bigger zone, and hence I can potentially leak more refrigerant. Because the concern is all of the refrigerant for the VRF somehow has a leak in one room, and that room happens to be the smallest room, and now all of the refrigerant for the whole system leaks into that one room. That's the concern. So you just don't use small rooms. Get a bigger room, right? Take the small rooms off the VRF. Or have one unit ducted to 2 of the small rooms. Now if the refrigerant's leaking in that ductless unit, half of it's going to one room, half is the other. That might change the math. Or put the unit above the ceiling so some of the leakage goes into that quantity. Don't use one big 40-ton VRF. Use 2 20-ton VRF building or loops, right? And now I've divided my problem in half. Don't have closed doors between some of these spaces if you don't need closed doors between the spaces. If you interconnect them, now my smallest space is a bigger space. Don't run a bunch of your pipes through a small room. Go around the small room with the piping, because not only could the evaporator coil leak, but the piping could leak. Now, all of these things are only if there's a bad leak somewhere, right? This is not likely to happen, but codes aren't developed for the usual scenario. They're developed for what's the worst case thing. That's why we have a code like this. So you got to do these tricks to get VRF into these buildings. I'm going to skip this, but there's a bunch of studies out there that you can look at. I'm referencing some here. ASHRAE has really good details because they did one whole floor of a building with GEO and another whole floor of their own building with VRF, and they can compare the energy usage on those 2 types of buildings. So that's a good one to look at. For folks up in Wisconsin, my friends at Slipstream, I know it says 7th Wave here. I got to change that. They changed their company name to Slipstream. But in any case, they have a really cool dashboard on their website where anyone in the general public can go look at live data on their building, which is a VRF geosystem. They have a geosystem that is VRF, which is really cool. And you can go look at the live data anytime you want. Anybody can. And the really cool thing about that, and you can't change stuff, by the way, on their building automation. You can only view it, obviously. But the really cool thing about that is people will email into them and say, hey, I noticed this weird thing happening over here on your one zone. It's almost like they got the whole world helping them troubleshoot, quirks, which is kind of cool. All right. So I do apologize. I went 14 minutes over. I apologize for that. Some things to consider. Bjorn is asking, for VRF, do I need a separate air handler for ventilation? That's a good point. I didn't bring that up. I should address that. So I'm going to go back to a slide that I can use to kind of help explain that. But for VRF, I still have the same rules for ventilation that I have for all the other buildings that we discussed, 2 weeks ago. So I still got to bring all that code-required ventilation air into the building. But here's the difference that I'm going to have. I don't have a system that does that easily. If I have an air handler, all I have to do is just say, okay, well, my economizer on my rooftop air handler, go to this minimum position, right? Okay, good. Outside air is covered for me. Well, these guys, they're not located outside and they don't have any ductwork. So getting fresh air into the building, I have three choices on what I can do. I can do operable windows. Many building codes allow natural ventilation, and I can use operable windows. Now, if I have a giant, huge building with an interior space that has no access to an outside wall, well, I can't do natural ventilation for that building, right? But if I have an older building where the building was designed with, like, say, you probably seen buildings like this, right, where there's an H shape to the building. Oh my God, my artistic skills are so bad, right? The reason they do that is so every zone is like within 15 feet of a perimeter, so they can all have a window. Or you might see buildings that had a courtyard, right? Now every single room has access to a window. And that's how they used to get their cooling on an old building. Before we had cooling systems, you had, steam radiators all over the place for heat. And when you wanted cooling, you opened up your window, right? So if that's your building, you could still do that natural ventilation. And now you can argue about whether natural ventilation is very effective or not. That's another debate. But you're still allowed to do that. A lot of the VRF systems get used in retrofit applications because those are the buildings where it's hard to run ductwork. So you're putting this in an old building because you couldn't get ductwork in. That old building may already be okay for natural ventilation. So that's one. I can use natural ventilation. The other things that I can do are I could have a separate system. So I can have this VRF system with all these zones doing cooling. Then I could have on my roof next to these guys, I could have what's called a dedicated outdoor air system. Another acronym for you. And this is a whole nother hour topic on its own, but a DAOS or a DOAS system, dedicated outdoor air system. And he brings 100% outside air in. A normal rooftop's bringing in 10, 20, 25%. This guy's bringing in 100% outside air. So he's designed to handle that. And he can still handle the dehumidification needs of that. He's specific to this. And then he is ducted in to each of the rooms. Now, this still does save me a lot of fan energy, which is why VRF is efficient anyway, the fan energy savings. But I still have more fan energy than just VRF by itself. But this guy now, instead of having, I'll make up a number. Instead of having a 40-inch duct running around the building, I got a 10-inch duct running around the building because he only does ventilation air. He doesn't do recirculation air. Recirculation air is happening locally with these guys, right? And then my VRF unit is either just has a little diffuser in the room, or maybe he's ducted into the back of these guys, right? Or ducted into these air handlers. You could do it that way as well. So I can have natural ventilation. I could have a DOAS unit that's bringing air into rooms, or I can have a DOAS unit that's bringing air into the backside of any of my VRF units. Let's see if we have any other questions. Mark asks, can we provide the name of the software tool you mentioned and showed comparing units for commercial and residential? Okay, so the one that we used last week and this week, this one looks like this. That one is called Commercial Invest. It used to be called RTU Invest, and then they changed it to Commercial Invest because you can do rooftops and split systems with it. And that software is provided by Carrier Corporation. So in order to get that, you would contact whoever your local carrier distributor is. If you happen to be in Chicago and the Chicago suburbs, that's my company, so call me. But if you're somewhere else, like if you're in Boston, you would contact DCNE, Distributor Corporation of New England. Carrier distributors have it. Bryant distributors have it. I think ICP has it as well. But that's that software tool. And as I mentioned last week, it runs on a software engine called HAP, Hourly Analysis Program, which is a very robust energy modeling tool. And this is just like a simplified interface to that engine. And it just does this thing, right? It just does a snapshot of this. The other tool does everything. It does load calcs, it models VRF, it models chillers, everything. This just does a snapshot, which is rooftops, but it uses the same calculation engine. The other tool that I used and showed was this one, right? That's probably the other one you're thinking of. Oops. This one is more residential. It is definitely residentially focused. And this one is actually, if you look down here, it's made by a company called RightSoft. And they have a very robust tool as well that does load calculations and all kinds of room by room modeling and all kinds of stuff like that. And this is just a simplified interface that they have in order to make it easy to do without modeling the whole building. So it's the same kind of idea that other one was doing, but it's for residential. This one is available. This particular one I was using was, well, Well, if you know the model numbers, this one was specific to Carrier as well. If you haven't figured it out, I'm a Carrier. I work at a Carrier distributor, but they make one for Carrier. They make one for Bryant. There's a similar tool, but different, not from RightSoft, that is available. That a lot of the guys that have like Tempstar and Heil and those guys use. So a lot of these are specific to the brand of the equipment. But you can put generic stuff in. Like on this, I put a generic, on one of the examples, I put a generic 10 SEER unit in. I don't care what brand it is. Doesn't matter to me, right? And then for the high-end ones, I pick specific model numbers because that's what I know. But you could do it that way. What else? Other questions? Now that I'm 20 minutes over? It's all Mark's fault. He asked an extra question. I'm just kidding, Mark. Thanks for the question. Okay, let's see. One more came in. I got to expand it because it's lengthy. Why can't I expand the window? Okay, why can't I expand my window? Oh, there we go. Sorry, when you guys type in long stuff, I got to blow up my window really big. Okay, so Shanarka says, thank you for the 3-part webinar. I'm a mechanical engineer, grad student from field industry. Do you have any words of wisdom for beginners starting out in this field? That's a completely loaded question that probably has a 3-hour webinar associated with it. But I guess the best thing I can say for anyone who's more of a beginner, meaning you're 1 or 2 years in the industry, the best thing I could say was don't assume that the old people in the room with you know what the hell's going on either, because they probably don't. They might be good at certain things, just like I'm only good at certain things. But what I've noticed a lot of times is people getting trained by the older guy at the office or the older gal at the office is that whatever bad habits and whatever misconceptions that person had get handed on to you. Whatever rules of thumb they were using that are old and outdated get handed down to you. Right? They're using a rule of thumb that they got from their mentor from 1960, gave it to them in 1980, and they're giving it to you in 2015. You're getting their old habits, right? So don't assume that they're right. Do some of your own research. Do things like we did today. Watch webinars like this. Just because the guy next to you says a heat pump isn't going to work in Boston might not be true. It might work just fine in Boston. In fact, it does. There's thousands of them installed in Boston right now. There's not tens of thousands like there is other types of equipment, but there's a lot of them, right? Same with anything else. Don't assume the other people know more than you. And once you get past that hump, then you start building up confidence. You can go find the answer yourself. And if you can find the same answer from a couple different sources, right, and then try it yourself, I guess that's my best advice, is don't assume everybody knows more than you, because they probably don't. And they certainly don't know more than you on every topic. All right. With that, I'm going to shut this recording down. If you have other things that you need, you are welcome to email me. I will put my email up one last time if I can figure out how to get off this screen. I don't know how to get off the screen. There we go. Discard that. Go back to the first slide because it had my email. So thanks again to the folks at MEEP, the folks at UMass, and that's my email down at the bottom if you want me to follow up with you on something. After the last 2 weeks, a bunch of you emailed me. I think I finally, after several days, got back to everybody. I still got a day job too. But I'll do the same thing. And sometime the next week, I'll read whatever you had and try my best to answer it and get you pointed in the right direction. So I thank you guys for your time. And Alberto thanks you for your time. And we'll see you guys at the next event.